Okay. Good morning, everybody, and welcome to the second day of the IRCDL 2021 conference. We are very happy to have you here, and today we will start with a session on information and knowledge. The first paper will be presented by Ornella Herrero, and the title is Background Linking, Joining Entity Linking with Learning to Rank Models. So, Ornella, please go on. Perfect. We can see your screen.
Thank you. Good morning, everybody. Today, I present the work I did with Professor Gianmaria Silvello. We focused on learning to rank. In particular, our goal was to study the impact of a set of entity-based features. We organized our discussion as follows. After a short introduction, we described the proposed solution and our experimental setup. Then we describe the results obtained, and we conclude with some considerations and the future works. We developed our work in the context of the background linking task belonging to Track News Track 2018. Its primary goal is to tackle the possible lack of context and background information users may have reading online news. In particular, the reference collection for this track was the Washington Post, which counts about 600,000 documents published in the Washington Post from 2012 to 2017. 50 topics were provided and 5 relevance grades were provided for this task. We relied on LambdaMart learning to rank algorithm because it is one of the best performing algorithm in learning to rank algorithm in the literature. And it has a list-wise approach, and it is based on multiple additive regression trees. In particular, we based our learning process on features extracted from 2 different representations of the same document, the original textual representation and a graph of entities. In particular, we think that the entities together with the relationships can give a valuable contribution in relevance identification. In the last 5 years, there are several solutions which involve entities or the combination of words and entities. But the most interesting to our case is the one proposed in 2017, where the combination of words and entities allowed to obtain excellent results. Our starting point is the creation of a baseline. In particular, we applied the BM25 model to our corpus, and according to the guidelines, we retrieved 100 documents per topic. This baseline is extremely important for 2 reasons. The first one is that we use the documents in this baseline as test set during the learning to rank task. While the second one is that the results of the baseline are a useful reference point to compare our results with. We firstly created for each document the related graph of entities. First of all, we performed entity linking in order to annotate the textual document with the Wikipedia entities. And we used this bag of entities to create an undirected weighted graph, whose vertices are the entities retrieved, and the edges are inserted on the base of the semantic relatedness existing between pairs of entities. At the end of this phase, we obtain a graph which is usually subdivided into connected components. In particular, the largest connected component is characterized by community structure, where there are the most meaningful and important entities for context identification, while the other minor connected components usually contains entities which derived by errors in our notation. This is why we want to perform pruning in order to discard all the out of context entities. and we kept only the largest connected component, and we run the Girvan-Newman algorithm for community detection in order to obtain the largest community where it is more probable to find the most meaningful entities. And let's see a practical example. This is a portion of an article about tropical storms. We firstly find the terms which have a corresponding Wikipedia entity, and these are the entities associated. This represent the entire textual content. And now we create the graph. Well, it is now possible to perform pruning. We firstly discard the minor connected component, which contains out-of-context entities. And then we run Girvan-Newman algorithm in order to remove Earth and explosion, which are too general for context identification. And we obtained our final graph. We extracted two sets of features to include in a document's vector representation. The first set is the textual-based set, which include features dependent of the query document, and these are BM25 score or the time frequency, but they can also be independent, and we can find the document length. The other set is the graph-based set, and also in this case we have query graph independent features, and in this case we have topological properties of the document's graph, such as the node connectivity. And we have the largest subset, which counts 43 features, that is the query graph-based set. And we show an example of this kind of features. We have two graphs, the query one and the document one, and we find running the betweenness centrality measure the most influential node in both the graphs. And we replace the most central entity of the query graph with the one of the document graph. And we compute the new semantic relateness between the document's central node with its new neighborhood. The final feature is the average of the new semantic relateness computed. And the higher this feature is, the more probable is that the document contain valuable context information about the query document. Then we run learning to rank, in particular, starting from a training set and an effective hyperparameter combination, we could automatically construct a ranking model. This is used by the ranking system to re-rank the documents belonging to a test set. In particular, we obtain as output a final run which contains the documents of the test set, but with a different ranking. The final phase of our implementation is the fusion. In particular, we considered at most 10 runs, the most belonging to the most effective models, and we combine them with the COMSUM method. This phase has two goals. The first one is to try to improve the retrieval results, and the second one is to study whether an increase in the number of runs fused can be corresponded by an effectiveness improvement. Let's see some technical details. We annotated each textual document with the TagMe RESTful API, and we annotated at most 30 entities for each document. This settings approach derives by a study conducted on 30 textual documents of the corpus. In particular, this leads to graphs with at most 30 entities. And we set a threshold on the edge insertion. This threshold equal to 0.4 is extremely important because it allows us to have a graph subdivided into connected components. And it allows us to have the most meaningful entities in a unique connected component. We trained LambdaMart with a training set composed of 21,000 vectors, and we used two disjointed sets of topics for training. One set was the one provided for the Common Core track of 2017, whose reference collection is the New York Times annotated corpus, while the other set is the one provided for the News Track 2019, whose reference collection is the Washington Post corpus. Even if training set and the test set share the same collection, that is the Washington Post corpus, the sets of topic we used were all disjointed. Even if introducing the New York Times collection allowed us to enlarge the training set, and so we can increase the accuracy of the learning process, it made our system suffer all the consequences brought by the transfer learning. In particular, the most influential one is the lack of consistency between relevance grades. In fact, we had to map the 5 relevance grades belonging to the Washington Post corpus to the 3 provided for the New York Times annotated corpus. Then we manually tuned the hyperparameters, and we selected the 70 models the best performing in terms of NDCG at cutoff 5 in the validation set. We firstly performed a quantitative analysis, which allowed us to study how our system performs on average. We reported the performances of the best models run, that is the best run, and then the best performing fusion runs, which correspond to the fusion of 2, 3, 5, 7, and 10 runs. And then we report also the performances of the baseline. If we consider an analysis of only one document per topics ranking, we can see that our system always outperforms the baseline. And in particular, the best performing run is the fusion of 5 runs. But if we study the performances of the topics rankings at different cutoffs, we can see that after 5 topics, 5 documents in ranking, our performances decrease as the number of documents considered increase. And this is partially caused by the transfer learning. If we can make a first consideration, in particular, the increase of the number of runs fused is not corresponded by an increase in the performances. In fact, the fusion of 10 runs is the least effective run. If we consider our primary measure of effectiveness, that is NDCG at 5 documents in ranking, we can see that the best models run approximates the results obtained by the baseline. And we can see why performing a qualitative analysis, which involves the specific topics, in our case, of the best models run. In particular, we represented an histogram where we represented the topics belonging to the best run, and for each topic we put into relation its results in terms of our best models performances and those of the baseline. In particular, above the abscissa, we can find all the topics where our system outperforms the baseline, and vice versa holds for topics below the abscissa. We can see that there is the same number of topics where our system prevails over the BM25 models, and the number of topics where BM25 models outperforms our baseline. And this allows us to understand that these two systems fits disjointed sets of topics. And there is never a system that always prevails over the other one. This analysis allowed us to understand what the advantages and the disadvantages are of our system. Starting from the advantages, we can see that the graphs played a crucial role for those topics in which our system prevailed. In particular, this topic showed in their rankings documents whose relevance was detected both from a point of view of graphs and from the point of view of textual features. And moreover, our system always manages to put in the first half of the ranking all the relevant documents. And it is particular a case of a topic whose relevant documents were only 6, and they were placed in the first 12 position of the ranking. For what concerns disadvantages instead, we can see that transfer learning has a strong impact in our implementation. In fact, it prevented some topic to reach their highest results. And it prevented also our system to perform in a good way after 5 documents in ranking. And moreover, we noticed that there are some errors during the learning process. In particular, sometimes the value of only one feature influenced the entire topic's ranking, and the remaining part of the vector was not taken into consideration. Finally, we could understand what the cases where it was convenient to use the BM25 model instead of our system. In particular, graph strongly depends on the textual content of a document. And if a document is relevant, but it contains a really short textual content, its graph could not represent its relevance in the best way. Moreover, we notice a case of a topic whose documents have all graphs similar to the query one, even if the documents were not relevant. In this case, all the bag of entities were similar, so the graphs recognized the general topic the documents were about, but the final information these articles want to give to the user was not detected in the graphs. And in these last 2 cases, it is always better to choose the BM25 model instead of our system. I conclude with some further researches that can be carried out to improve our current system. The first one is the performance of an automatic tuning, and the other one is performing an ablation study discarding the textual-based features, and in order to understand what the real impact of graphs is. And I conclude. Thank you.
Thank you very much, Ornella. Thank you also for being on time. Is there any question for Ornella? Sorry, I'm not sure that I see one. Okay. No, I don't see any hand that is raised. So I have a question, and in the meantime, if somebody else wants to have a question, it just has to raise the hand, and I will give him the word. So Ornella, I was wondering, what is the meaning of the relevance in the graph? I mean, the weight that indicates the relevance. Is it computed on the basis of the specific document or of the relationship that exists between these entities in a bunch of documents? You see what
the relevance of a graph, of a document in graph can be detected both from the point of view of the bag of entities, but the most important thing is the relationships which exist between entities. So it is a combination of the entities which represent the document, but also the relationships. Because
yes, my question was about the relationship. So the weight of the relationships. I was wondering, how do you compute the weight, you see, of the relationships? Yeah.
We computed it with the definition of semantic relatedness provided by TAGME, and it identifies the semantic relatedness that exists between 2 entities, and it identifies the similarity. Was this the question?
Yes, but this similarity, is it computed on the basis of a big set of documents or on the basis of the single document that you are considering?
on the basis of the single document we are considering, because we firstly extract the entities and then we compute the similarity between entities, between pairs of entities.
Okay, okay, I see.
Yeah, but Antonella, how do you calculate the similarity? I think this is Antonella's question.
Well,
I mean,
yes.
what do you use to calculate the semantic similarity between the entities? Or TAGME, what does TAGME use?
TAGME uses the definition we can find in the literature of semantic relatedness, which is based on the incoming link on Wikipedia pages. So it is computed between pairs of entities.
I see. So a relationship that is of type instance of is considered exactly as another relationship between, let's say, brothers, let's say some relationship between entities, single entities that you could have in a graph on instances. Yes? Okay, I see. Okay. Okay, because this makes a little bit difference now, because I mean, if you, I saw that you skipped HERF because it was too general, storm, HERF.
Yes.
But probably there was a relationship of type instance of, and this kind of relationship is very different from the relationship that says he lives in.
Yes, that's true. But we were interested in the entities that could contextualize the original document at best. So we were more interested in the semantic relatedness, and we performed the discarding of the entities on the base of this measure.
Okay, okay, thank you. Is there some other, are there some other questions? No. Okay, you can also write on the chat if you prefer. Okay, so let's go for this, to the second paper. The second paper will be presented by Giuseppe Lancioni. And the title is Efficient Key Phrase Generation with GANs. It's another long paper. Go on,
okay.
Giuseppe, thank you.
Thank you, and I'll share my screen. You see my screen? Okay. And yes, I am Giuseppe Lancioni, and I am a PhD student at the University of Udine, iLab, Artificial Intelligence Laboratory at the University of Udine, while starting presentation. And I'll speak to you about efficient key phrase generation with GANs, a work of which Professor Serra, that is my supervisor, is a co-author. And yes, let me to introduce the key phrases with an intuition. We all in our daily work, we read scientific documents, mainly scientific documents, and generally speaking, we underline some parts of the text that we feel as representative of the reading. And also we annotate the doc, that is, we generate some short phrases that, in our view, summarize some sentences or some part of the document itself. So all in all, our key phrases are short text sequences that convey the main semantic content of a document. So a sort of summarizing, but not exactly summarizing, of the source document, of the document we are reading. Here, a brief example. We have the title and abstract of a scientific document, and at the bottom we have the list of the key phrases. All but the last are key phrases that are contained inside the document. So you could imagine that for all but the last, we have underlined these phrases, the short phrases on the text. The last is one about the general meaning of the document. So we could imagine that we have written some note in the margin of the paper. By a more formal point of view and a formal problem definition, we could say that documents and the relative key phrases are pairs, X and Y, where X is the document and Y is a set of the n-related key phrases linked to the document. And we could refer to this set of key phrases as the true key phrases, or if you want, the target key phrases, or the the human curated ground truth, and so on. And consider that both X and the generic key phrase, one of these, is made of words. Both are sequences of words of different length, as you can see. So the task of a key phrase generation model is to take as input the document X and to generate a new set of key phrases we will call Y circumflexed, that is a set of M different key phrases, with the aim to reproduce the real one, so that Y circumflexed be equal to Y. We will refer to the generated key phrases or the predicted key phrases with the name fake key phrases to split them from the true key phrases. Then our approach was to introduce the GAN architecture. GAN architecture, generative adversarial networks, has been introduced by Goodfellow et al. In 2014 in computer vision, mainly in computer vision, and it obtained outstanding results in computer vision. More recently has been introduced also in natural language processing tasks, so in tasks with text generation. But in this case, we have to slightly change, not so slightly change the architecture. Generally speaking, it is a GAN architecture is made by two different networks that works together and that are trained together. The generator G, generally speaking, it is an encoder-decoder model that is able to generate text, so an encoder-decoder model for text generation. In our case, we used the CATSEC model introduced by Yuan et al. In 2018. That is an encoder-decoder model for text generation optimized for key phrase generation. So it is the state-of-the-art model for key phrase generation. It is widely used in many systems. It is the base of many systems in key phrase generation. Then there is another network, the discriminator, that basically is a binary classifier that is able to split the real key phrases from the fake ones. So it has to classify the samples he is evaluating by saying this is made by generated, so fake key phrases, this is made by real or human curated key phrases. We used and we introduced, I think for the first time, the BERT model, a BERT pre-trained model with fine-tuning for sequence classification, as we have to classify the whole pair, source text, and related key phrases. BERT is part of the transformer architecture. It's introduced by Devlin in 2018, and it is the encoder part of the transformer architecture, and it leverages on the attention mechanism, only attention mechanism. The paper that introduced the transformer, the title is beautiful, is all you need is attention. No convolution, no recurrent neural networks, only linear layers and attention mechanism. Then one problem arises as the GANs, you can't straightforward apply a GAN architecture in text generation because there is a well-known problem about the differentiability of the argmax function. So a technical question, a technical issue that needs to be addressed in some way, for example, by using reinforcement learning. So in this case, in the general case, GANs are trained with a min-max optimization function. So you train both generator and discriminator together, for example, in computer vision. In this case, we can't train together the generator and the discriminator. We have different sessions of training for the generator and for the discriminator, but using reinforcement learning, the generator is trained using the reward given by the discriminator. Now I'll show you more in detail this architecture. This is our proposed architecture. Here you have the generator, here the discriminator. First step is to train a first version of the generator. So this is the very first version of the generator trained in the canonical way using maximum likelihood loss and using the real samples. You see the pairs, document, and related key phrases. Once trained, the generator, the first version of the generator is able to generate key phrases that are the fake key phrases, and both fake key phrases generated by the generator and real key phrases are given to the discriminator to train the discriminator. The discriminator is trained with mean square error loss, as it has to classify these samples. In particular, it performs a regression of these samples. That is, the target value is 1 for the true samples and 0 for the fake samples. So the higher the regression score the discriminator will evaluate, the more probably the sample will be real. The lower the regression score evaluated by the discriminator, the more probably the sample will be fake. Then it evaluates the regression score, and then this regression score is given back as a reward to the generator. And from this step on, training is made by different iterations of generator and discriminator, but the generator is no more trained with maximum likelihood, with maximum likelihood, but is trained with reinforcement learning schema, that is the optimization function, the objective function to optimize contains the reward, that is the regression score given by the discriminator. The generator tries to maximize this reward, that is, tries to learn to generate more realistic key phrases that will be evaluated with a nice score by the discriminator. And so this is the overall system and the training schema. Okay, in particular, the discriminator, we introduce a BERT model, a pre-trained BERT-based uncased with 12 layers, 12 different blocks of that are exactly the same as a structure, but they are in a sequence of 12 blocks or layers with 12 attention heads, and it generates embeddings with 768 components for each of the input token. BERT is a positional embedding, so each of the input token correspond in the same position the output token. In detail, the first phase is the pre-processing, that is the sample are lowercase, tokenized using BERT tokenizer, and also special tokens are added, the initial special tokens and the final special tokens. And we also add the separator special tokens to separate the document part from the concatenation of the key phrases. Key phrases are concatenated with the semicolon. Then once pre-processed, these samples are passed inside, are given as input to BERT. BERT is pre-trained, but in this case, pre-training acts as an initialization of the weights, as during training also the BERT weights are trained. So there is a training also for the BERT model. The output is aggregated together to have one semantic representation, one embedding of the whole input samples. And then the last layer is the layer that evaluates the regression score. This regression score will be given back as a feedback to the generator during the generator reinforcement learning training. Generator tries to maximize this reward, that is, and doing so, it learns to generate more realistic key phrases. Datasets we use, just a bit about the datasets. The most important is KP20 key, introduced by Ruimeng and et al. In 2017. It is by far the most used now, and it is a very large data set, more than 500,000 samples that consists in concatenation, in union of title and abstract from paper about computer science, of which 20,000 are used for validation, 20,000 for testing, and the remaining more than 500,000 are used for training. This is the canonical training data set. All the models that uses the CAT-SEC generated model, encoded-decoded model that we use also use the 500,000 samples for training, but we were able to train our system only with 2,000 of these samples. So we obtained data efficiency in this way. Then there are 4 other data sets, well-known data sets in the key phrase generation field topic that are used only for testing. So one data set used for training and the same data set and the other for testing. And about the results, we made the comparison with the 4 state-of-the-art models, all employing the CAT-SEC model, because we would like to compare with the same, in some way, the same architecture. And we obtain promising results, by far the best value in terms of F1 score for the INSPECT dataset, and we almost match the best result for CEMEVAL, and we almost match also other values, for example, F1 top 5 or F1 overall. F1 top 5 always for CEMEVAL, and we are close for NAS and also for Crepidin. And then we also perform a ranking score with respect to the original model, CAT-SEC, trained with the canonical 500,000 sample dataset. And we obtain, in terms of the ranking scores, mean absolute precision and DCG, normalized discounted cumulative gain. We obtain an improvement in the retrieval of the key phrase with respect to the original model. So that's all.
Thank you, Giuseppe. Thank you to you too for being on time. Are there some questions for Giuseppe? Yes, thank you, Stefano Marchesin.
Hi, Giuseppe. Thanks for the presentation. I was curious about one thing. So you mentioned that basically you train the generator at first in a regular fashion, and then you introduce the reinforcement learning approach. So my point was, so basically at the beginning, from my understanding, when you do the GAN approach, you try to introduce noise, and then you try to maximize the difference between the noise and the correct labels. But then from what I understood, in the end, you're basically using, at the end of the overall training, the generator to generate the final keywords. Is that correct?
Yes, you use the generated key phrases. The general aim of a GAN is to train the generator. It is the most important part of the architecture, but you have to also take care of the discriminator. So how to train the discriminator? We pass to the discriminator samples that are made by the source document and the generated key phrases, and the source document and the real key phrases. And we train the discriminator saying that the corresponding value, target value is 1 for the real key phrases and 0 for the other. So we have a balanced system in this way, because for the same source document, we have the generated key phrase version, that is the fake version, and the real one. Okay. I don't know if
okay. Yeah, perfect. Thank you.
Alessia? Alessia Bardi also has a question.
Yes, hello. Thank you very much for this presentation, Giuseppe. So I wanted to ask if you see any issue that would prevent you to run your approach on a set of documents that are not of the same discipline, because you said that you used only computer science documents. And what if you had a much larger set of, domain with mixed domain, so like 150 million abstract to work on? What would you change?
Okay, in my opinion, most of the works up to now about key frame generation are about scientific documents, and in particular computer science. The 5 data sets I cited in the presentation were really the canonical ones used in key frame generation. But in the last few years or months, there are some interesting work about, for example, articles of newspapers. So general information, we could say. How would perform our architecture in this case? I think we need to change in some way the training, because we were able to obtain data efficiency because we were in a well-known field, that is the scientific publication about computer science. In that case, I think we would need to take more samples for training our system. It is necessary, I think, in this case.
Thank you.
Okay, thank you. So now we will view a video that was sent by Luca Piazzon to present the next paper, because Luca could not attend the conference. So the title of the paper is S-Aware, Using Award Judgments in Supervised Measure-Based Methods for ER Evaluation. So please, Stefano, you can...
Sure. Let me open it, and then please notify me if everything works, because I hope everything goes smooth. But let's see.
Okay, thank you.
Okay, can everybody see the screen?
Yes.
Okay, perfect.
So, yeah. Mm-hmm.
Okay.
Good morning, everyone.
Thank you.
I'm Luca Piazzon, and unfortunately, I can't be live with you today. So we decided to go for a recorded video, but feel free to contact me if you want to know more about this work or if you have any questions. I will present the work done together with Nicola Ferro and Marco Ferrante, named S-Aware, using crowd judgments in supervised measure-based methods for IR evaluation. This is an extended abstract of the work recently presented at the Conference and Labs of the Evaluation Forum in September 2020. And the goal of this work is the development of a set of supervised algorithms for the usage of crowd-assessed judgments for the evaluation of information retrieval systems. In this presentation, I will first introduce the motivations behind the usage of crowdsourcing methods, passing then to the description of our algorithms, of the experiments and the relative outcomes. In the field of information retrieval, a good method to evaluate information retrieval systems is crucial for their improvement. To do this, it is necessary to use experimental collections, where for each document is assigned a relevance judgment, usually given by an expert assessor. This classical methodology for test collection creations is, however, quite onerous in terms of time and costs. A modern approach instead relies on judgments coming from a larger number of less qualified assessors, called crowd assessors, that are then used together in place of expert judgments. The collection of crowd judgments is largely faster and cheaper, but can be affected by spam judgments. The classic usage of crowd judgments is to combine them at pool level, obtaining a merged pool that can be used as ground truth for the evaluation tasks. Two major examples of these methodologies are majority vote and expectation maximization. Majority vote is the simpler one. For each topic document pair takes the judgment given by the majority of the crowd assessors. Expectation maximization instead iteratively estimates the probability of relevance of the documents and at convergence assigns to each document the most probable judgment. Merging crowd judgments at pool level has one main weakness. A single error at pool level can cause different effects on different performance measures computed on the run coming from the systems. Let's consider this toy example where there is a single mislabeled document and retrieved at position 2. Here, a single error at pool level that corresponds to a 20% error in the pool can cause errors on measures from 19 to 50%. To avoid this problem, in our methods, we follow a different approach. Instead of combining the crowd assessors at pool level, we compute the evaluation measures based independently on each crowd pool, and we combine these measures, weighting each assessor with an accuracy coefficient that estimates the skills level of each crowd assessor. These accuracy scores can be computed in different ways. In our previous work, we presented an unsupervised version of AWARE, and the information retrieval systems were evaluated according to each crowd assessor and according to 3 fake random assessors that randomly assigns the relevance judgment to a document with different probabilities. These measures were compared using some dissimilarity measures. So the more the crowd assessor behavior is far from the random ones, the higher accuracy is assigned to the assessor. In our work, instead, we used a set of supervised estimators of crowd assessor accuracy. In this case, the crowd assessor measures are compared on a training set of topics with the measures computed on the gold pool. These measures are compared using some similarity measures. So the more a crowd assessor is near to the gold standard behavior on training topics, the higher accuracy is assigned to the assessor. We consider the values of an evaluation measure computed on a set of runs coming from a set of information retrieval systems for a set of training topics, and we denote this as M. And we consider also the measures computed with respect to the gold standard, and we denote this as M star. We propose 2 approaches to compute the similarity between the assessor and the gold standard. The first one is to compute the root mean squared error between the assessor measures and the gold measures. Small values, or RMSE, are mapped to high accuracy values. The second approach involved the ranking of the systems induced by the computed measures and computes the Kendall-Stau correlation between the assessor ranking and the gold ranking. We consider then 3 levels of sharpness of the accuracy scores, taking the square and the cube values to increase the discrimination among good and bad assessors. To test the effectiveness of our methods, we compared them against some common methods as majority vote and expectation maximization, the Georgescu-Zhou algorithm that uses the expectation maximization to predict assessor confidence, the Tang-Li's semi-supervised version of expectation maximization that makes use of a set of gold labeled documents, the uniform AWARE method that assigns the same accuracy to each assessor, and the best performing unsupervised AWARE methods. We use the average precision as evaluation measure. We use the runs coming from track 8, track 13, and track 26 as systems, and we combine groups of 2 to 7 assessors. Since gold training data is expensive to obtain in a rare case scenario, we use the very challenging fraction between training and test set, using only 30% of the documents as training set. The experiments are performed considering all the possible combination of parameters and repeated 100 times for validation purposes. We use 2 different datasets. A first set of assessors comes from the participating pools of track 21, and we have 31 complete sets of judgments of 50 of the topics used in track 8 and track 13. To better fit to a real case scenario where each crowd assessor judges only a portion of the dataset, we considered also a set of artificially partitioned assessors, each of them taking judgments from different original crowd assessors, simulating a more fragmented situation. The second dataset is the one assessed by Inet et al. That collected judgments coming from 406 assessors on track 26 topics. And to use this data in our experiments, we grouped these assessors to obtain a set of partitioned assessors similar to the one I mentioned before. Let's move to the experimental results. Once obtained the final measures according to each method, we computed the p-correlation between the ranking of the systems induced by each method and the ranking induced by the gold standard measures. Let's firstly consider the original complete pools from track 21, that is clearly the most favorable case for S-aware. This plot represents the p-correlation value trends while increasing the number of merged assessors. We see that S-aware with cubed Kendall-Tau similarity constantly outperforms all the other approaches, even when we combine a small group of assessors. We can observe that Kendall-Tau performs better than RMC as closeness quantification, and that the cubed weighting typically gains some more performance. Both unsupervised and supervised aware outperform the most part of the baselines. Moving to the partitioned assessor, here we have the plot about the experiments on the Inet et al. Dataset. We can see that in this case, the gap between the S-aware and the unsupervised aware becomes smaller, but S-aware still outperform in most cases its unsupervised version. In general, S-aware still outperform both the unsupervised and the semi-supervised baselines. Also in this case, the squared and the cubed version of the accuracy scores achieve a better performance since they emphasize more sharply the difference between good and bad assessors. In this table are reported all the results of our experiments. On the left, we have the system. On the top, we have all the tested methods. Both values are the best performing methods for each row. We see that in general, S-aware and unsupervised aware are always contending for the first place, and this strengthens our motivations to combine assessor at measure level and not at pool level. Let's go to the conclusions. Even using a very few training data, S-aware mostly outperform all the other tested approaches. But as expected, the capability of S-aware to correctly estimate the assessor accuracy decreases when dealing with the fragmented assessors. Both unsupervised and supervised aware in general outperform all the set of baselines. A future extension of this work on both supervised and unsupervised approaches will try to compute an accuracy score for each sub-assessor, avoiding the need to group fragmented assessors as we have done here for partitioned assessors. Thank you for your attention.
So thank you. Luca is not here, but Nicola is a co-author. So if there are some questions, Nicola would be happy to answer. Otherwise, you can also contact Luca later.
Okay, then welcome to the section character recognition, and the first paper is titled "A Qualitative and Quantitative Approach to OCR Error Detection Correlation in All Newspapers for Corpus Assisted Discourse Studies." And the paper will be presented by the authors, Dario Delfante and Giorgio Maria Di Nunzio. Then please start.
So good morning and thank you for having us here. I am Dario Delfante and this is a project I work on with Professor Giorgio Maria Di Nunzio within my PhD project. And this is a very brief overview of the presentation, what we are going to present. And so basically, it's important to start from the research aims. So considering that we were dealing with the corrupted OCR dataset, and so with historical data, we needed to develop an ad hoc detection and correction procedure for OCR errors in order to make our dataset machine readable and usable. But before that, it's important to contextualize which is the theoretical and methodological framework in which this project lies. So, which is corpus linguistic and corpus assisted discourse studies, which is basically the interest, the study of language through corpus computer software in order to uncover non-obvious meanings, unexpected pattern of language. And so it's a kind of distant approach to language, a distant view to language. And it can be corpus-driven, so an inductive approach or corpus-based approach. And specifically, the theoretical and methodological framework which I have work is the corpus linguistic historical, historical diachronic perspective on language. So we are interested in studying the past through corpora. So there are different kinds of applications, and there are different kinds of frameworks. Etymology, there are applications to history and social sciences, and the study of the past has many kind of implications and many kind of aspects which need to be justified and defined before the research. But one of the examples, for example, one of the possible study of historical corpus linguistics is, for example, the frequency distribution over time of a specific word. In this case, we have the word pretty. The corpus is the Iyibo. This is an example taken from a book by Brezina, 2018. And in this case, as you can see from the table, the corpus has been like split into decades, and the calculation is made per million words, and it's a relative frequency. And this shows like the distribution over time, how it changes. The word changes. So there are very different applications, but it's important when we approach like diachronic corpus assisted discourse studies that we need to think about three aspects about like of the corpus in relation to the corpus compilation. The first thing is the historical representativeness. So the fact that the sample, a corpus is always a sample of language. A corpus is not all the entire language expressed by a specific time. So the sample has to be historically representative. So it has not to be biased. There are a lot of reflection and discussion, but it's important. The second thing is structure of the corpus. So you have to adapt the structure of the corpus you are going to produce and compile. So the structure has to fit with the research aims and the research goals. For example, if you are looking at, depending on the level of linguistic analysis, for example, you have to structure like to divide in decades or per years or per month. It depends on your aims. The third aspect is the semantic change to which language is devoted. So language changes during time, and the perspective from which you look at the language of the past from today is a kind of perspective which doesn't fit with the perspective of the people of the past. It's very simple and quite normal to say that, but this has to be taken into account during the analysis. So, but the second aspect, so the second most important thing is the fact that when we speak about historical corpora, we are in front of old texts. And old texts which have not been digitized, okay? So, and there are different types of old texts. In this case, we are in front of manuscripts or old private letters. And for our case study, we work with newspapers. So as you can see, different format, different shapes, different kind of paper. And when you compile an historical corpus, you need to digitize these texts. And the digitization has many issues. So the first is the quality of the camera, the image compression algorithm, the quality of the paper, And these things all contribute to the like resulting TXT file, which come from the OCR scanning. And as you can see from this slide, on the left side, we have the article taken from La Stampa archive, and on the right side we have the resulting TXT file, which is heavy damaged by like a lot of LCR post-processing errors. For this reason, we needed to produce like a procedure. Anyway, this is the overall project. So this procedure has been applied to a specific study. So the study was aimed to study the representation of the metaphorical representation of migration from the United States of America and Italy between the beginning of the 20th century and the beginning of the 21st century. So the area was very restricted to a specific case. And the approach we developed is divided into 3 stages. So the first one was the corpus creation, the second was the OCR detection and definition of rules, and the third one was the OCR correction and quality analysis. Let's move on. So corpus creation, as I already mentioned, is very important. And before that, we thought about how many texts we could retrieve for the research purposes. So to have like a satisfiable data set to detect metaphors. So for this reason, we decided to narrow down and to restrict the number of documents, also to have a more manageable corpus. And so we selected 2 sets of search terms, an English one and Italian one, which were produced by looking at different texts of migration from the 20th century and from the beginning of the 21st century, in order to have like to retrieve only those documents which were on migration. And so these were the data set, the data sources, 2 for the old corpora, and 1 from LexisNexis from the contemporary corpora. So this table shows you the resulting corpora. So the first 2 are the old corpora, New York Herald and La Stampa corpus. And the second one are the New York Times corpus and La Stampa corpus. So the first detail which like captured our attention was the ratio between the type and the tokens. As you can see, is very high, unexpectedly high for the old corpora, whilst the contemporary corpora is quite normal, in line with the expected results. It's important to say that the contemporary corpora, New York Times and La Stampa, were already originally produced in a digital format. So these don't contain any OCR error. And the high number of the type duration of types, as you can see from the table, is due to the OCR errors, which are counted as a single like word, a single type. Anyway, so let's move on. So we, at the second step after the corpus compilation was the OCR detection, so error detection. And we decided to use a semi-automatic mixed approach. So like a dictionary-based procedure and a context-based procedure, in order to capture the most number of errors possible. 2 types of errors, of OCR errors we identified: non-word errors, so invalid lexicon entries which are not attested in any dictionary of the analyzed language, and real-word errors, so valid words which are in the wrong context, like fraud of irritants or other kind of errors. So this is like the 3-step procedure through which we identified and produced the list of like rules, definition of rules. So at first, we produce a list of errors through the dictionary-based approach I showed you before. So before we did not have a corresponding digitized truth version of our old corpora, we used the contemporary corpus, which was correct. And so we compare through a keywords analysis the old corpus with the old corpora with the contemporary corpora, because our hypothesis was that the resulting keywords analysis, keywords list would be related to the number of errors, because the contemporary should be without any kind of error. So after this list of candidates, we analyzed qualitatively each error of this list through the context-based analysis, the collocation analysis, in order to detect and to define if this list of errors were all like errors. So we produce a list of detected errors, we categorize step to these errors, and then we define for each error identified a correction rule, which then was applied to the corpus now. Yes.
Okay, so we use this mixed approach with user feedback to correct errors. Then just like a clarification, in some cases you can use OCR correction softwares that use contexts to understand what could be the most probable word that is corrupted in a sense. In our case, the OCR scans are so badly corrupted that even the context is corrupted. So it really is a first pass that we are doing in this project. So in order to at least figure out a way to correct some parts of the text, and some others will not be possible to correct it in any case, because it's too difficult to understand even reading the original scan. So we use this approach in order to be as reproducible as possible with our language. It's called approach, uses this tidyverse approach, which is, in other words, a set of packages that you can combine in order to import the text and clean the text, and then produce a document that shows you all the steps that you have done. Next, please. So this is just an example of this markdown file that, if you're used to Python, it's a sort of notebook file where you can mix text that describes what you're doing and code. So it's a sort of runnable text code where you can document every step, and you have also the output of every step in order to be reproducible. Next. So basically, we use these 4 steps that correspond more or less to 4 packages. We import the text, we tokenize the text using some very basic rule. Well, here, instead of filtering, here you can see it's just a reuse of the same code that we used for another experiment, where instead of filtering words, we just correct the words. So we do not stem or we do not lemmatize words. We just try to find the exact character sequence that was suggested by the user, in this case, Dario, and then we started to count. And then we sort of compare the count of each token that we find in the corrupted corpus with the reference corpus. And if there is a big difference in counts, in relative frequencies, then Dario starts to analyze whether that is an error or just a very infrequent or unlikely word in the corpus. Next. So this is just a very short and small example of what we mean by writing manually the rule of the correction. So, for example, for the standard error, these are the errors that contain the exact same number of characters. So, for example, the first row is olla, which is corrected to alla. And by the way, you can just see for this that we will introduce for sure some, let's say, false positive errors, in the sense that there may be situations where olla, it might be a true word, a real word in the original text, but we anyway correct it into alla without having any context available. So we try to correct in any case. So we are introducing by default with this approach some false positive errors, and this is part of the analysis that we are going to do in the future, and some other non-standard errors that you can see. For example, click the first row of the bottom part of the table is just the H that has been represented or interpreted by the OCR interpreter as the LI as the shape of the H. And in that case, again, we are going to transform click into K in any case. Next. So this is the result. Starting from the bottom of this page, we found so far 476 errors for English, and by the way, it's done manually. So it's a feedback. I give Dario the results of the numbers. Dario tries to understand whether that is an error or not, and write the rules. I implement the rule, and then I do this feedback again. Much less errors for the Italian corpora, just because the quality of the scans of the Italian papers are much better than the English ones. And then you can see we made hundreds of thousands of substitutions for English and a few tens of thousands for substitution for Italian. So even so, we were able to semi-automatically correct many portions of the documents that still have plenty of errors and will have for sure some false positive errors that we introduced unintentionally or partially intentionally because we knew that. So I will give the floor to Dario for the conclusion.
So like this, we think that this semi-automatic approach for correcting OCR errors developed for this project has proved to be effective. And I also believe that this procedure and the set of rules can be reproduced and reused for different contexts. So within the same language, but for example, for different time periods or different language domains. So not newspapers, but in medical language, other kind of like political language, sport language, but also for different languages. This is our aim. Also, comparison of our analysis with recent approaches that make use of BERT pre-trained neural networks to post-hoc error correction made us think that we need to also consider new paths, new ways. And another thing we want to understand is we want to investigate how many documents that we missed during the compilation of the corpus in the first step. Given that a search keyword as we produce may be subject as well to OCR correction as well, because the documents in the data sources you saw are stored in OCR TXT for OCR TXT format. So this may be problematic. Thank you very much for the attention.
Thanks, Dario and Giorgio, also for being time and for the presentation, of course. Are there any questions? Just check on the participant list. I start with one. First of all, I'd like to know, you mentioned that you check the total number of words that appear in a document with the correct one, and then if this value is different, the difference is large, you check what's happened. I want to know which is the percentage of this kind of the percentage when you decide to check or not.
Okay, you mean the keywords and the posture when we compare the two lists? Yeah. Do you mean, okay? So was it was based on log ratio? We used the log ratio, and we just put as a cutoff, we just decided to look at the first 300 words in the list. So there wasn't a very specific cutoff point, but generally the difference was no frequent word in the contemporary corpus, frequent word in the old corpus. So all the words, the first 300 words were all words that did not appear in the contemporary corpus and did appear in the old corpus. So that was the difference.
Okay, then another question, very small question is, when you design rules, you need some particular expertise, you need to know, you have to know very well the domain that you are working on, or...
Yeah, I mean, like, I use contextual information, and I mean, you have to be. I mean, I'm a linguist now. I'm a linguist, so that was my expertise, and also that I was expert in newspaper language, and for this reason, I have like a knowledge of what I was going to do. But also the contextual information are very important. So I made a lot of use of the context to decide if it was an error or not.
And just for clarification, we found with students, working with the students, some examples. Now I forgot that one was interesting, like they thought it was a mistake in the OCR conversion. Instead was a word that was used in Italian at the beginning of the 20th century. Like, I don't know, like on top of my head, I have the gioco del calcio. It may sound very odd. It's not that word, but these are unusual or words that are not used anymore that may be considered wrong, but in that context, in the case, we're correct. So yes, you need a lot of expertise in that sense, and you have to see that vocabulary of that particular period.
Okay, then thanks again.
Thank you.
And we move to the second talk of this section. And it's a short paper, and I give the floor to Raphael and Malin.
Thank you so much. We, Rafaela, Anders Hast, and I, Malin Navark, we're very happy to be here to present a work in progress, which can also be described as an early step toward the solving of what in a Swedish context is a literary mystery of great significance. So Astrid Lindgren, who is a Swedish author of children's books, holds a unique position within world literature. Her enigmatic creative process has for many years been hidden, however, in her original drafts and manuscripts, which are all written in the stenographic system of Melin shorthand, which is based on the Gabelsberger system. So in Sweden, these supposedly indecipherable original drafts have to a large extent contributed to Lindgren's creative process being surrounded by myth. Another factor in this myth-making relates to the role that Astrid Lindgren played in the production process of her own books. So the year after her breakthrough with Pippi Longstocking, which is represented up there in the right corner, Lindgren was employed by her publishing house and became her own editor and publisher. So Lindgren used shorthand both for writing and editing. Consequently, her shorthand notepads is the only first-hand source to the development of her literary work. Next slide, please. So these shorthand notepads, which contain Lindgren's literary production from the 1930s to the 90s, are mostly kept at the Astrid Lindgren archives at the National Library of Sweden. And they have for long been considered extremely difficult and time-consuming to access. They have never been subject to research. Within our ongoing interdisciplinary project, the Astrid Lindgren Code, we have digitized 55 out of 670 notepads, primarily containing shorthand drafts and manuscripts to the novel The Brothers Lionheart from 1973. Next slide, please. And the main purpose of the Astrid Lindgren Code project is the deciphering of Lindgren's stenography through mixed methods. So that is HTR, applied and developed in interactive combination with collective transcription through volunteer expert sourcing. So together with an expert group of stenographers, we recently successfully started to transcribe selected material manually in order to produce the transcriptions that we need for future alignment. So that is the introduction to what we're doing, and I'm now going to give the word to Rafaela.
Thank you. So moving on, I would like to cover a couple of aspects, challenges and opportunities from a handwritten text recognition point of view. Starting off with the fact that we are facing a clean slate So there is very little HDR research on stenography in general, and there is no existing approaches for Gabelsberger-based stenography, which we have in this case with the Median system. In addition to this, we are working with a low resource corpus, essentially. On the one hand, it requires highly trained stenographers to transcribe this, this data set or this manuscript. In addition to that, the already existing transcriptions or that are being produced at the moment are not yet aligned with our page or word images. Moving on, I would like to give you a brief overview of what we've been working on so far, starting with our pre-processing pipeline. On the left here, you can see the images as we receive them from the archive after they've been digitized. In our first step, we crop out these bindings and some superfluous edges here to receive a very focused page image. Here in the zoomed in version, you can see most of the pages are written in a gray lead pencil, and all of the pages have printed on them a red ruling running over the page. So one of the steps in our pre-processing pipeline is the removal of the background, as well as the removal of these red rulings to avoid distractions, which you can see here on the third image. In this step, we also detect connected components to then use for the extraction or segmentation of our words. Here's the zoomed in version then of the next pre-processing step. And finally, on the right, we have our extracted words, which we place in these uniform bounding boxes, and we arrange them such that the original red ruling runs through the center here, indicated by this green line. And if we had ascenders, like is the case here, then they would of course run further down. Once we have these images, we're currently working on a semi-automatic transcription approach based on clustering. So starting out with our images, either using them directly or applying some form of feature extraction like histogram of oriented gradients or a CNN, we feed these images or features into a dimensionality reduction technique, be it TSNE, UMAP, what have you, resulting in a 2D image of data points. So each point here corresponds to one image in our original data set. On top of our 2D space, we apply a kernel density estimate, and then of the resulting surface, on the inverted surface, we apply a watershed to segment the individual clusters. Here on the left, we show a summary of each of the clusters in the form of a heat map of the contained images. And if we, for example, take this cluster here, we can reapply the clustering approach or the dimensionality reduction approach on the contained images to receive a more fine-grained view here. And taking, for example, this bottom right cluster as an example, these are all of the images that are contained in here. So each data point, again, corresponds to one image. And the numbers up here are just identifiers, so not of relevance further. And as you can see, this selected cluster here is already very clean, and most of the words are in fact the same, in this case spelling out Jonathan. And we intend to use this approach in a interactive user interface, which is currently under development, to select individual clusters, clean them possibly a bit, and then annotate in bulk these dozens of images at once as Jonathan. So in conclusion, we have shown early results or a work in progress, which show that Lindgren stenography can in fact be transcribed semi or fully automatically even. And in the future, we intend to expand our work to other HDR approaches, such as, for example, CNNs, and then ultimately automate or augment the transcription process for the remaining roughly 600 manuscripts. And with that, I thank you, and we're happy to take questions.
Okay, thanks. Thanks for the presentation, for being time, of course. And are there any questions? Okay, I have in the chat. No. No. Okay. I have a question. I understand that you are using some reduction dimensionality algorithm, and I think you use to move your data from a high-dimensional space to two. I was wondering if you did some experiment try to reduce dimensionality not just for 2 but for 3, 4, 5 and see what happened.
Not yet. At the moment, we've been focusing on 2D, which is quite it's fairly easy to segment, and it's easier to work with from a user point of view. But that's definitely an interesting idea to look into in the future.
Okay, then thanks again. And we move to the last speaker of this session. And the title of the paper is Location of Simple Graphemes in Medieval Manuscript Based on a Masked IRCDL. And the authors are Simone Marinai, Gabriella Pomaro, Claudio Raffaelli, and Francesco Scandifio. Okay, please start.
Okay, good morning. My name is Claudia, and my colleague Francesco and I will be presenting the work for the realization of a system aimed at the localization of simple graphemes in medieval manuscript, which is all based on a masked CNN network. We will be seeing what is the goal, some data gathering issues that we faced while collecting the documents for building our dataset, the model based on masked CNN, as we were saying, and some analysis and results. The framework we developed has the goal of providing useful tools for paleographers for the dating of Latin Middle Ages manuscripts. In fact, while in the process of dating a document, scholars in the field of paleography, among other things, look for specific graphics clues within a manuscript. Because of the fact that graphic signs change slowly over the centuries, they represent a trace of how writing has changed. The graphemes can be then used to provide a time frame for when a document was written. However, some writing style lasted for so long time or were so widespread they could not provide any useful information for dating. But still, there are some specific significant graphic variants whose presence or absence is critical to scholars for the dating of a manuscript. It is clear that this described process is very long and prone to human error, and an occurrence of a search sign could be missed or there could be a misreading. When manuscript consists of a large number of pages, and we're talking about hundreds of pages, it is very difficult to carefully inspect all of them and in an accurate manner. This will be an extremely time-consuming task. In fact, only a small amount of sample pages is analyzed in order to extract the already mentioned information. It is easy to see how this kind of approach can lead to incorrect dating results. This is also because copying a manuscript often took years of time. During this time frame, the amanuensis could change its writing style several times. For this reason, an automated system capable of locating certain paleographic letters within a collection of documents can be of particular use. And as a side note, the manuscript used for the training of the network are all gathered from the Codex archive built by the International Society for Study of Medieval Latin Culture, which is with the aid of other online libraries. And we selected the documents giving precedence to those originated from Tuscany. So a good share of the available documents presented excessive signs of wear, such as burns, rubs, and tears, which limited the amount of manuscript that were suitable for our task. Here we see an example of a manuscript page that presents such problematics, but that has, however, still deemed acceptable. Here we can see that there are regions with color contrast, a portion of paper with reflected light, faded strokes, and slightly crumpled paper. This is also the case with the manuscript page that presents such problematics. Here we can see that there are regions with color contrast, a portion of paper with reflected light, faded strokes, and slightly crumpled paper. Moreover, online libraries of ancient documents usually expose only low-quality images to the public. In this example, we can see an image that is kind of a borderline case regarding the quality of the pages we accepted for our purposes. The grainy appearance of the letter is an element that can hinder the success of the recognition. It is clear that all these factors influence the quantity and the quality of the images available. The occurrences of the graphemes of interest have been manually labeled through the annotation program Interactive Label Me, and the output JSON collects all the polygonal segmentation, and it has been converted into the common object in context format for ease of use with our architecture. Since characters are usually drawn very close to each other, some annotations contain the grapheme of interest together with fragments of close signs. This implies that this is present some noise in some of the segmentation. That is, however, very limited and acceptable. Here in the picture, the Interactive Label Me interface during the process of annotation of a manuscript page. On the center, the annotated page, and on the right, the list of the labeled occurrences. As we were saying, there are some graphemes more significant than others, that allow the dating of a document depending on their presence or absence within the manuscript. Here are the selected 12 graphic variants. We observed that in the manuscript pages before and the images here that the quality of the pages is highly variable. Some graphemes are sharp, with dark strokes on a light background, facilitating operation of recognition and possible banalization, while others, such as the Zeta and the Tia Sibilata, are very grainy. Other, again, present little contrast between the stroke of the grapheme and the background, complicating even further the recognition. It should also be noted that in general have been collected few examples for some classes of letters, leading to a set of annotation rather unbalanced in favor of some of them. In particular, we also have introduced the grapheme Tia Sibilata, the annotation work already begun. For this reason, even though this is an interesting letter variance for the dating, since there are no sufficient examples of it in our dataset, it wasn't taken into consideration during the analysis process, but it will be better handled in our future work. We move now to talk about the network used. Our work is based upon MaskRCNN, which is one state-of-the-art deep convolutional neural network used for object detection and image segmentation. MaskRCNN extends faster RCNN and is composed by a standard convolutional neural network for image classification and by an additional fully convolutional network for semantic segmentation at a pixel level and on proposed regions. In particular, the network goes through two main stages. The first one is responsible for generating on the input image a set of proposals about the regions where there might be an object. The second stage is related to the output produced by the network and allows the classification of the proposal suggested at the previous stage. This also allows bounding boxes and mask generation. The output of the network is a bounding box enclosing the recognized object and a pixel mask that is placed on it. In particular, we adopted Detectron 2, which is an implementation of MaskRCNN, and it has been made by the Facebook AI research group as our architecture.
The model we present was obtained by applying the fine-tuning paradigm, which consists of initializing the weights with a pre-trained model and tuning the hyperparameters in order to find the combination that gives the best results. The Detectron developers provide some checkpoints with which to initialize an instance of the network and then train it on a custom dataset. In particular, we chose a ResNet with 50 layers based on FPN backbone and trained for 37 epochs on the COCO dataset. This model has been chosen because, among those supported by MaskRCNN, it offers the best speed-accuracy trade-off, as pointed out also by the developers. COCO means Common Object in Context, and it's a dataset for the recognition of animals, vehicles, and objects from the everyday life. Even if these objects have nothing to do with latent graphemes, this kind of approach is useful when dealing with data scarce problems like the one under discussion. After deciding on the model, we proceeded with tuning the learning parameters. In particular, we focused on learning rate and max number of iterations. In order to identify the optimal learning rate, we have carried out 69 independent trainings composed of 500 iterations each, increasing the learning rate at each new training. When we then compare the learning loss, selecting the learning rate with the highest variation towards the minimum value. We also evaluated different scheduling policies by comparing precision, recall, and FA1 measure on the validation set following a trial and error approach. The best results have been achieved by training the network with a fixed learning rate at 0.0035. Once the learning rate was established, we started a long training session during which we ran an inference task on the validation set every 50 iterations. With this experiment, we have found a number of iterations that achieves an adequate balance between precision and recall while avoiding overfitting. In the figure, we see a comparison between the predictions made by the network as the number of iterations increases. On the right side, we see that confidence and precision are greater, but recall is halved. This means that the model is overfitting. Indeed, graphemes of the same class are written in different ways over the dataset, even between pages of the same manuscript. We can therefore find letters with different lengths and sizes depending on the hand of the writer. For example, at the very beginning of the research, we have found that learning on pages from a single manuscript led to poor results on documents from other books because of this difference in style. The experiment related to parameter selection were repeated in 4 different scenarios, resulting in the model summarized in the table. We distinguish between networks trained on the latest version of the dataset, H-code, and those trained with the small dataset using the very first phase of the research, identified by L-code. We also wondered whether the amount of data of the new dataset was enough to abandon the pre-trained approach, code 1. Thus, we tested model trained from scratch with a random weight initialization, code 0. The dataset currently consists of 49 pages of documents, 11 of which are labeled. These 11 pages are the only one that can be used as ground truth for experiments, and we therefore divided into 5 for validation and 6 for testing. The remaining ones were all used for training. Regarding the first version of the dataset, this is composed of only 25% of the actual annotations. In Latin, as well as in other languages, some graphemes appear more frequently than others. The different probabilities of occurrence strongly influence the availability of data, skewing the sample distribution in favor of the most frequent classes. The table shows the number of labeled graphemes grouped by class. We note that S dritta and the tonda variants are the most common, constituting 70% of the available instances. This imbalance leads the network to learn more features related to the most frequent signs while ignoring the least common. It is therefore reasonable to expect that the results of the classes at the bottom of the table will perform worse. The analysis was carried out by comparing the precision, recall, and FA1 measure of the 4 models. The work carried out about training has been a continuous balancing process between precision and recall. Even with the same network, by changing the lower limit of confidence on the proposals, we can increase either precision or recall. Ideally, we would like to increase both at the same time, but they usually move in the opposite direction. The results we present have a precision about 85% and a recall of around 50%. Comparing these values with the current method of searching for graphemes, that is by hand, even finding the 50% of the occurrences within an inference of few tenths of seconds provides paleographers with useful information in a short time. When comparing the models, it is evident that the networks initialized with the pre-calculated weights perform better than their from-scratch counterpart. This is in line with what we said earlier, that is, the fine-tuning paradigm is useful when training with little data. so we do not yet have enough examples to be able to proceed in a totally satisfactory way with learning from scratch. Comparing the results of all the networks, 1L and 0L models obtain the best scores, ranking first and second respectively for F1 measure on the test set. From these values, it may seem that the models trained on the first dataset are better than those on the updated version. This will mean that the update of the dataset made things worse, but is it true? Let us go in a little more detail about this point. The table on slide 15 shows the precision recall results for each class individually. From the comparison, we see that the network trained on the first dataset, the one on the left, has better scores, but is only able to recognize 1/3 of the graphemes of interest. This means that the network has a high score on the most frequent classes, but only because the imbalance of the examples was so strong that all the other classes were insignificant. Model H1 learned the feature of 2/3 of the classes, and this shows that updating the dataset was useful. We observe that the recognition of new classes is paired with a lower recall on the most graphemes, so this network is less specialized than the one on the left. Finally, as expected, the classes at the bottom of the table have the worst scores, and some are not even recognized. Even if the update of the dataset has moved things in the right direction, further efforts needs to be made to achieve 100% coverage and to reduce the variance in recall between classes. So to conclude, 1 minute recap. The aim was to help paleographers in dating medieval manuscripts by implementing an automatic grapheme recognition system. This work was carried out by training a masked CNN neural network. During the construction of the dataset, the problem of data scarcity emerged. This problem has been addressed using the fine-tuning paradigm. Indeed, among the model tested, the pre-trained variants gave the best results. From scratch networks are also promising, but further work needs to be done to consolidate the use of this kind of approach. Regarding the imbalance problem, it might be useful to increase the examples of the rarest classes through data augmentation technique. Finally, a graphical interface is essential to allow the model to be used by a wide audience, and we are currently working on it. In the end, we would like to thank those who supported this research. Fondazione Cassa di Risparmio di Firenze, Dinfo at University of Florence, and SISMA. Thank you for your attention, and we will be pleased to answer any question.
And thanks for your presentation, for being time. Okay, are there any questions? Any question?
Yes. Hello everyone, I'm Nicola Barbuti. I would ask, it's an interesting work, an interesting experimentation. I'm asking how paleographs can use this kind of tools, or which kind of studies, which kind of research, and if this this kind of tools are able to train a big collection of manuscripts images.
Okay, I will answer. Okay, then. Okay, yes, we are currently working on creating a graphical interface in order to allow the paleographers to look at the results of the inference of the network, and in order to see how many of certain classes of letters are found. And by doing so, I'm not a paleographer expert, but they can give a date or to a manuscript by looking at this information.
By comparing graphs in different types of manuscripts?
By looking at how many letters of a same class there are within a manuscript, they can understand the date of a manuscript.
Maybe Gabriella can give more answer.
Yes, she's our.
She's connected. Gabriella, vuoi parlare?
She told me that she has
audio,
technical
issues.
Yeah,
I see. She's talking, but will not hear her. So maybe you can continue.
Yeah. Okay. Then.
Okay, for me. Thank you. It's fine. Thank you.
Thanks again. Thanks for all the speakers for this section. We are just close the section.
Okay, it's 11:05. I think if Gian Maria agrees, we can start. Okay. Okay, so the first presenter is going to be Eleonora Benasconi from Sapienza. It's work on exploring a text corpus via knowledge graph. So you're already set, so please, thank you.
Thank you. Good morning. I am a PhD student in engineering in computer science at Sapienza University of Rome. And in this presentation, first of all, we talk about the digital humanities research field, and in particular about the visual search and exploration of digital cultural artifacts. Subsequently, I will show you the ARCA prototype that allows the visual search and exploration of a catalog of books. I will propose you the results of an evaluation of the system, and finally, I will present you future developments. The digital humanities is a new discipline emerging in 2000s with the huge developments in communication technologies and the digital revolution. Digital humanities is a crossover discipline connecting the social sciences like anthropology, philosophy, archaeology, and the other with the computer science. Traditionally, humanities scholars carrying out research on specific or multiple literary works are interested in the analysis of related texts or text passages, and the digital age has opened possibilities for scholars to enhance their traditional workflow. Enabled by digitization projects, humanities scholars can nowadays reach a large number of digitized text through web portals such as Google Books. This shift from reading a book on paper to the possibility of browsing many digital text is one of the origins and principal pillars of the digital humanities domain, which helps to develop solutions to handle vast amount of cultural heritage data. In contrast to traditional methods, the digital humanities allow to pose new research questions on cultural heritage datasets. Some of these questions regard visual semantic search and exploration of an existing text corpus. In the following slides, I want to show you the first attempts made to create the visual search interfaces. Then I want to describe the modern methods and techniques to visually explore a source of textual documents. I will present you some research questions and hypotheses on the basis of which I built the prototype for the visual semantic search and exploration of digital documents. The first attempts to create a visual search interface have been done in the early 1990s, where some researchers had applied a direct manipulation principle to search interfaces, creating what they call dynamic queries. These are visual query systems, and in particular query by example, namely search interfaces where users can manipulate sliders or other graphical controls to change search parameters, and where the results of those changes are immediately displayed to them in some sort of visualization. In 2013, Gale platform used an algorithm that creates mathematical representation of documents based on whether words appear in the documents and the relative frequency. Subsequently, Topic Graph tool aims to help scholars who are searching for books on a topic and understand to decide whether a given book is relevant enough to merit reading in full. But the issue of this type of visual searching tools is that each document is analyzed as a bag of words. The algorithms do not take into account any syntax or structure in the documents, nor do they attempt to infer the meaning of any given word in its context. To attach semantics to unstructured data, some relevant results have been obtained by exploiting the name entity recognition, the name entity linking, and the knowledge graph techniques. After the text is extracted from books and sentences are split, the name entity recognition identifies and classifies the concept present in the text, grouping them into predefined categories such as the name of people, organization, places, etc. Then the name entity linking technique classifies and disambiguates the meanings of the identified concepts. Thanks to the NER and the NEL techniques, text may be automatically associated with entities in some reference knowledge graphs. The knowledge graphs organize information around concepts which are connected to each other through semantic relationships. But if on the one hand, enabling knowledge extraction by these techniques may introduce some important advantages, on the other hand, it is afflicted by some intrinsic challenges. For example, first of all, the difficulty and time needed to implement a system that integrates these technologies. Another big issue is that these technologies, to work at their best, need an interface that is usable and adaptable to the specific domain of the text corpus. At the moment, various systems use these technologies. One of these is, for example, UNO discovered that it is an integrated system that offers classification and visual exploration of academic materials to help scholars in their research. UNO shows the concept sought in an interactive knowledge graph, but doesn't show the semantic relationship between concepts. In this way, the researchers aren't able to understand immediately the connections that relate one concept to the other concept. Instead, in the ARCA prototype, this feature is included. Another system is GlobeDef. It works with pluggable enhancement modules, which are dynamically activated to create on-the-fly pipeline for their enhancement. But the problem with GlobeDef is that GlobeDef carries out a semantic enrichment challenge, but stops there. The ARCA prototype also includes the management of the generated metadata, the integration with existing knowledge graphs, and the visual exploration of this data through a unique visualization. Another system is Apache Stumble, which is a set of components for semantic content management. Instead, in the ARCA system, we propose an integrated system that allows the exploration of a knowledge graph through a unique visualization. To date, there is no visual search service that can be automatically adapted to a source of selected text. This is the main feature of the ARCA system, the adaptability of the visual search engine to any textual content through a unique visualization. The goal of the research is to try to answer some questions, some research questions, and to sustain some hypotheses. The first research question is, would the user exploring a corpus of text profit from the semantic navigation of the associated knowledge graph of topics? And what kind of user interface would effectively support such navigation? The hypothesis is that users will be able to effectively explore a text corpus through a knowledge graph-based user interface, which offers the following main functions. The first is find concept through text search, then visually navigate the concepts and their relationships, and finally show documents relevant to the selected concept. Another research question is, what kind of users, scenarios, and tasks would benefit from this interaction paradigm? The hypothesis is that this method will benefit both users with little knowledge of the domain by supporting semantically relevant discovery, and then users who are the main experts by enable topic-oriented visual organization of the documents. The last research question is, does building and maintaining a semantic enrichment and knowledge graph creation pipeline necessarily involve high upfront costs and highly skilled developers? The hypothesis is that it is feasible to build a ready-to-use complete system, including both semantic enrichment pipeline and a web-based front-end, able with only some configuration to be applied to any specific corpus, to enable the knowledge graph-based exploration. To answer this research question and sustain the hypothesis, we implement a pipeline composed of four steps. In the first step, the content of the document, for example, the PDFs, is stored in the system along with the relevant metadata. In the current version, the documents are loaded by copying them in a directory, but the plan is to generalize the method by having a repository that supports the linked data container API. This repository will be maintained by the catalog maintainers, for example, editors or librarians, through a dedicated front-end application. It will also be possible to connect it directly with existing databases or system for automatic content insertion and update. In the second step, the documents are analyzed by a set of semantic enrichment services that give as output the knowledge extracted from the content expressed using existing models and knowledge graphs. Currently, a service providing entity extraction is called. The results is a set of recognized entities identified as DBpedia link, alongside the point in the document in which the entity was found. An adapter converts this information to RDF standard so that it can be later integrated with existing metadata and DBpedia knowledge graph. In the third step, both the metadata coming from the linked data container and the knowledge extracted in the previous step are stored in the triple store as an integrated knowledge graph. Due to the distributed network of linked data, relevant additional external data may be either added to the triple store in this step or kept separated and accessed on demand when needed. Finally, the front-end is able to integrate on-the-fly data from the local triple store and other linked data sources. In this specific use case, the data from DBpedia is integrated on demand, so that the Explore Knowledge Graph is a virtual graph obtained by merging the local knowledge graph with the DBpedia knowledge graph. The interface packs 11 features listed in the right column. The first feature is the login, which allows the user activity tracing. Then the search bar component allows to search for topics or books that a user is interested in. One concept can be explored. For example, one can observe in which books the concept is contained. With greater relevance or not, can find all the semantic connection inserted in the IRC and knowledge graph and DBpedia knowledge graph. Then with the trace path tool, we can find the concept in common of two selected resources. In this case, it's find books that contain both the Roman ancient city and Roma's divine concept. We can drag and drop all the entities in the board and explore it. Then the books button shows the books which contain the selected concept. In this case, the selected concept is Rome. And we can drag and drop on the board all the books that we are interested in, as you can see in the video. Continue to browse the knowledge graph and to explore all the books. Then there is the info of the books and the snippets of the books, which are the sentences of the books which contain the selected concept and the selected entity. Then it is possible to see all the list of books contained in the IRCA system, the history and the chronology of the user searches. And so the user can drag all the resources that previously find. And the final components are the legend and the video tutorial button, which can help the user to navigate and explore the interface. The tool is being tested on 112 books. The collection of this data have been done in 3 ways: an evaluation of the quality of the identity extraction, a direct observation of the user interaction with the system, and an online questionnaire. These techniques have allowed collecting qualitative and quantitative data And the participants includes in the user test a group of researcher experts on the topics mentioned in the catalog of books. The system obtained a more than satisfactory performance in recommending relevant editorial products and received a high score in terms of the usability, the simplicity of use, the user satisfaction with the results shown, the consistency of the contents with the book's domain of the publishing house, and the attractiveness of the system. Nonetheless, the evaluation highlighted some issues that need to be addressed in the future versions. Many of these issues stem from the quality of entity extraction. The issues can be grouped into 4 macro categories: wrong resolution of acronyms and abbreviations, the attribution of Latin words or other languages traced back to English or Italian, incorrect disambiguation of entities due to the absence of the correct entity in the DPPD knowledge graph, and finally, the wrong OCR reading. So, users complain about a relatively small amount of information in the internal knowledge graph, built with the concept of only 112 books and the related metadata. It is expected that when the catalog of books is numerically more significant, the chance of discovering new information and connections while browsing the knowledge graph will increase. Finally, based on the initial observation, it has been seen that using the system at first glance can be difficult without viewing the video tutorials. As a lighter alternative to video tutorials, a help component could be implemented to accompany the user in the first searches, and thus make him independent in exploiting all the possibility of exploration that the system offers. Feedback gathered from the users suggests that the proposed exploration mechanism tends to amplify the user experience by also offering opportunities for further study and discoveries of sources, terms, and materials which have the potential of enriching the research process with new ideas. The next step of this research will be research on how users can exploit a knowledge graph, in particular the interaction between users and knowledge graph to find information. Research on the storytelling applied to digital humanities, in particular integrate the knowledge graph with images and other media, and build a creative story generation prototype to be integrated into the currently developed prototype. Research on the possibility to allow users to add information into knowledge graph directly to the interface. And finally, perform a second user-centered evaluation with a classroom of students. In this slide are depicted some references, and thank you for your attention.
Okay, great. Thank you very much, Eleonora, for being perfectly on time. Any questions from the audience? You can raise your hand or open your mic. Just wait a few seconds. Okay, Maristella, yes, please.
It's not a question, it's just to say to Eleonora that has made a very, very good, excellent presentation.
Thank you so much.
Very professional and very involving the person looking at it. And you have presented a project that is related to a project I was working, let's say, 30 years ago, and we were not able to present in different levels also graphically our results, and your presentation is like a continuation of what we were considering with the explicit model. So I'm very glad. I'm very glad to see.
Thank you so much.
Any other comments? Okay, can I ask you just one thing? It's I really like the idea of using this linked data, the visualization of linked data, but and it's not nothing against your work. It's just a problem that I have. As soon as I open or link too many things, it seems to me useless in the sense that I cannot find the information that I need as soon as I open too many links or I connect too many links. Do you have any feedback from the questionnaire that you shared, or what was your what were the people who compiled the questionnaire? Were they experts in the field or students or?
The people is students, a classroom of students, also the researchers on the topic of the books containing the IRCA now. And they complain about some issues that I explain, but the global results is that the IRCA system has a very potential to help also the students and the researchers into their research.
Okay, thank you very much.
Thank you.
Okay, so 20 minutes, so it's 11:25, perfect timing for Stefano Ferilli for the next presentation. It's toward automatic floor plan interpretation. I think yes, you can share, perfect. Please go on.
Thank you, Giorgio. Good morning. I will present a work in which we tried to handle, in this case, floor plan documents, collections of floor plan documents, trying to go beyond simple recognition of components or of the overall kind of floor plan by using an actual interpretation of its content. After introducing and motivating this research, I will discuss and present our approach to floor plan interpretation and its specific steps, including, among others, furniture identification, room recognition, and then the actual plan interpretation. I have to stress the fact that this is a prototype aimed at showing that it is feasible and what it is feasible concerning specifically the use of reasoning techniques in the interpretation step. So the preliminary steps like furniture identification or room recognition are not to be considered as the state-of-the-art techniques for carrying out those steps, but just something that could help us in reaching the final step, which was our real focus. Then I will conclude and outline some future work issues. So we think that a true understanding of the logical and semantic structure of documents is very important, both for really understanding the content of single documents, but also to enable higher level tasks on document collections. For instance, retrieval, browsing, question answering, and a number of semantic activities that can be carried out on collections of documents to grasp a high level understanding also of the overall content of a repository. In this kind of perspective, we think that technical documents are particularly interesting and challenging. So actually, I'm in the text processing session, but I'm an outlier. I'm there by contraposition because I'm trying to use everything but text in document interpretation. And in this case, technical documents are interesting because their content, their meaning is hidden and implicit in the graphics. And while sometimes vector graphics are used, especially for creating the diagrams, actually what is really available is often a raster version of the documents, which adds challenges to the task, because in this case, we don't only lack metadata which can be added to vector graphics, but we even lack the real structures of the graphics and have to recover it by preprocessing techniques. So our aim is to improve the usefulness, the usefulness of formal reasoning approaches in technical documents understanding. This falls in the general area of document image analysis and understanding. And here we found that most approaches work only at the syntactic level, and at most they just scratch the surface of the real semantic level. So they typically label single, simple, or aggregate components of the documents of the whole documents. But we think that a full support to final users might include a help to interpreting the document and also to carry out additional inferences on those documents. I will provide some examples in a few slides. In particular, we focused on floor plan as a kind of technical documents because floor plans are much more widespread than other kinds of documents, and they have an interesting feature that they may start and interest and so require interpretations both by highly skilled technical people, but they can be interpreted also by the layman, let's say by everyday people, for instance, trying to guess how their house might be organized. So, as I said, well, it's not just a proof of concept because we actually implemented the prototype, but we just focused on proving what could be done. And so we also used quick and dirty techniques in our pipeline, not aimed at ensuring the best results. This is a very simple example of a clinic floor plan, which I will use in the end, but just to give an idea, in the end to show, to discuss a little bit the results. So our processing pipeline consists of the following steps. A low-level image preprocessing to just enhance the image, then walls identification, floor plan segmentation to identify relevant objects, non-structural objects, and then symbol recognition to label them according to their class, usually a furniture type of class. And then we may describe what we have found in these steps using symbolic descriptions, especially first-order logic ones, because relationships are extremely important in understanding floor plans. And then we will apply reasoning at the moment just to understand the kind of floor plan, but in general also to carry out more advanced kind of inferences and to draw more interesting conclusions. Preprocessing basically consists of two steps. Binarization, because the relevant information in floor plans is basically in the structure, so we may safely scale down to black and white images. In particular, we use the traditional OTSU method for this, for automatic thresholding. And edge enhancement, when we use a combination of OTSU and Sobel's approaches to obtain a negative copy of the image to mix again with the original image and try and enhance the edges, which are those revealing the structural and non-structural components in the floor plan. Concerning walls removal, we assume that walls are continuous, thick and solid black lines used to partition the space, and they are obviously the largest connected components in the floor plan. So we first extract all candidate components, which are those having a size above average, and then since some furniture objects might be attached to the walls and we want to only get the walls, we erode and delete twice the result and then subtract the walls from the original image. What I have to say here is that while other approaches use walls, wall detection to identify the spaces, the locations, the rooms in the floor plan, we don't just use walls, but walls are just one of the components which allow and help us to identify locations and rooms, because we may identify several locations within one room based on the spatial organization of furniture. Concerning image segmentation, we obtain it by region growing. We use a four-connected approach to region growing, and we use it because it's less dependent on image size and does not require a threshold, because floor plans coming from different sources may have different resolution, size, and so on. Basically, the three phases we use for our black and white binarized images are background expansion, by which we, starting from a background pixel, find the most part of the background. Then, in what is not included in the background, we iteratively select a foreground pixel, expand it, and consider the result as an object. For this object, we compute the bounding box and copy it into a new image by also removing all objects whose bounding box is smaller than 3 × 3 pixels as a form of very simple noise reduction. Once we have these objects, we have to classify them. Our symbol recognition, we adopt a symbol recognition approach, so we see object recognition as object classification, and we adopted a neural network, standard neural network approach for this. So we extract feature vectors from each object image, which is a color image if we extract it from the original document. We resize it so as to normalize it to 100 × 100 pixels size. We center the image with respect to every dimension, to both dimensions, partition it into 16 regions, 25 by 25, and for each of the 25 columns and for each of the 25 rows, we compute the average main channel value, red, green, and blue, and mix them by this formula. So basically, we get a decimal number where the first 3 digits concern the average red, the next the green, and finally the last, the blue. Finally, we just concatenate these 16 vectors of 50 elements, obtaining an input vector of 800 values, which is our input feature vector, while as an output feature vector representing the class of each object in the training set, we use a one-hot vector sized 200, which is the number of classes to be recognized. Very quickly, our artificial neural network is a multi-layer perception with 3 layers. The input and output layers were just the same as the examples, and the hidden layer included 500 neurons using a sigmoid function. The output values of neurons were in the 0-1 range, and so we had to, of course, normalize the feature vectors for this. Our training consisted of 500 epochs. Here you may find some details, but in the paper you may find more. What's important is that we also allow our network to avoid recognizing objects. So we recognize an object only if its output neuron has value greater than 0.9. We trained this artificial neural network on 188 images, which are 47 items, furniture items drawn from our dataset, each represented in 4 orientations. This is about 10% of our dataset of furniture objects, and applied to the remaining 90% furniture objects, we obtain 96% correct labels. To improve the result of the next phases, which are the most interesting to us, we fixed manually wrong classifications. Of course, the good results are due to the fact that the training and test set were very stable as a distribution taken from the very same set of objects. Okay, as to floor plan interpretation, as said, our goal is understanding the type of building based only on graphical information, so shape, furniture objects, types, and organization, without considering possible text in the floor plan expressing explicitly the kind of room or whatever. So our strategy consists of two steps. The first step focuses on locations, so identifying locations starting from the kind, number, and organization of furniture objects and of the previously detected walls, and then identifying combinations of these locations that may identify a kind of building. In particular, in this experiment, we focused on living room, on 5 kinds of floor plans. And for instance, a living room, a kitchen, a bathroom, and a bedroom in a given disposition might identify an apartment. As regards our first order logic representation, we focused on 3 kinds of concepts in our conceptualization. The physical objects, which are all the structural and non-structural furniture objects recognized in the previous steps, locations, meaningful spaces or rooms in the floor plan, and the whole plan. We think this is a quite general conceptualization which can satisfactorily express a number of possible situations and can be easily extended for more complex floor plans or objectives. These are the predicates we used for describing the basic information coming from preprocessing. So each object has a unique identifier, and we described its type of furniture, its direction in case it has an orientation, the full bounding box and the center of the bounding box, plus a parameter we provide to the next steps, which is the maximum distance, which may be provided manually or automatically computed from the floor plan, the maximum distance by which objects can be considered as belonging, adjacent objects can be considered as belonging to the same location. This is, of course, crucial. Based on facts built on these predicates, we use 75 rules divided in different groups and, of course, at lower or higher level of abstraction to carry out basically our understanding task. So understand when 2 objects might belong to the same locations, infer mutual positions of objects starting from their coordinates, describe spatial organizations and aggregates of objects, describe possible locations and possible kinds of plans. Here we focused for this experiment on 5 kinds of plans, which are apartments, classrooms, clinics, restaurants, and cinemas. So the interesting part of this approach is that while in this experiment we manually provided for testing purposes the rules may be also learned automatically, and this will significantly increase the flexibility of our approach. Our dataset consisted of 30 floor plans, and our approach was able to correctly recognize 26 of them. For the other 4, we understood that some of our rules were overly specific because they were not recognized due to some missing furniture objects or dispositions of the objects. This is the output, actually the first step of the output. Under the floor plan, we see which are a list of the recognized environments and a list of the physical objects for which we recognized those environments. So for instance, we recognized 3 bathrooms, patient bathrooms in the clinic, each of them thanks to those 3 objects, which are toilet, shower, and sink for 3 times. A waiting room, 3 patient rooms, and so on. So by clicking on these rows, we may have a human understandable explanation of this recognition. So I think this is a clinic because I found these and these and these locations, and these and these and these locations were identified based on these reasoning considerations. So we think that These results are promising to the general goal of understanding and the interpretation of floor plans and in general technical documents. We would like to carry out future work for improving and refining the technique, stepping from a demonstrator to a more reliable system, and add information for carrying out additional interpretations, not just the kind of floor plan. For instance, given a floor plan of a building, of an institutional building, understanding whether it is compliant or not, or what to do to make it compliant if it is not compliant to norms and regulations about, for instance, safety of the people in this period, for checking whether it is COVID compliant, and so on and so forth. Thank you for listening.
Thank you very much, Stefano. I think we have 1 minute for questions, if you have a quick one. Okay, I have a very quick one about the training of your neural network. If I'm not wrong, you said that you had a little bit less than 200 images rotated northwest.
Yes, exactly. Actually 47 images and then 188 images, because each image was rotated 4 times.
Mm-hmm. And do you think using some kind of, let's say, sort of standard procedure for training neural networks, like stretching or changing a little bit the shape in order to have more data, would help in that case? Or is it not just reasonable in the sense that floor plans have that structure, so unless you have a very bad scan or whatever?
Of course, this was a quick and dirty technique, because we just worked on our data set of 30 floor plans. And so our objective was moving quickly and efficiently towards the latest step. So, yes, for sure, we may improve general learning in case we aim at applying this strategy to real world tasks. We have to identify which kind of modifications to apply. For instance, stretching, I'm not sure, since object representations in floor plan is very standard. Well, you have different standards, but each of them has a very strict representation. I'm not sure that stretching is useful specifically, but for sure other additional kinds of modification other than just rotation will be definitely needed for learning, given especially the importance of object recognition to the later step.
Yes. Okay. Thank you very much.
Thank you.
Okay. I think we are just 1 minute late for the last presentation by Dennis Dosso. It's a short paper, so we'll have 10 minutes.
All right.
Great. Okay. We can see your screen. Thank you.
Perfect. Thank you. So, hello everyone. I'm Dennis Dosso. I am a postdoc researcher at the University of Padua. And today I'm going to talk to you a little bit about data credit distribution. So I will very quickly discuss about data citation and one of its limits. I will talk about data credit, how we performed our experiments, and then we will conclude with our future work. So, data citation. We already saw during this edition of IRCDL that we today live in the fourth paradigm of science. Data are very important for our research, and for this reason we need to be able to use data in our papers, but also to be able to cite them. In particular, we need to treat data in the same way, possibly, in which we treat regular scientific publication. We need to be able to cite them. Of course, data citation is a work in progress. We are still working on the protocols, on the tools, on the software, and there are, of course, some limits to it. One of these limits is that we cite what we see. What do I mean by this? Well, when we perform a data citation, we are using a query. This query produces an output, and we are citing that output. Of course, oftentimes what happens with queries is that they use more data with respect to the one that we see in the output. So when we cite the output of a query, we are not citing all the data that have been used by the query itself. So those data and all the authors and data curators that have worked on those data, they do not receive any citation, or more in general, any form of reward for their work. So what can we do about this? This is our idea to try to overcome this limitation: data credit, and data credit distribution. So we start from a database, from a query on this database, identifying data that we are trying to cite, and from credit. Now, credit is simply a real value which is describing the importance of this citation. So, for example, we have a paper, we have a data citation in this paper. The credit represents somehow the impact, the importance, the relevance of this citation in the economy, in the overall economy of a paper. Now, in this context, we are considering the credit as given. We are not focusing on how to compute it. There are different ways to do that. Now, the first thing that we do is to compute the data provenance. So provenance is a form of metadata for data, and it helps to understand how data was created, from where it comes from, its life cycle. And there are different forms of data provenance, but we focus on the forms of data provenance that help us to understand from where the data are coming, which parts of the input database are responsible for the production of the output. Once we have this provenance, we can compute what we call distribution strategy. It is a function, it is a plan, if we want to call it in this way, that help us to understand how to distribute this credit into the database. That is, we have this quantity of credit, this budget, if we want, we divide it in portions, and we annotate the data in the database, only the data that are relevant, that were used by the query, with this credit. And as I was saying, there are different types of data provenance, and in particular, we focus on lineage, one of the first types of provenance that were defined. It is defined as the set of all and only the data in the input database that had a role in the production of the output. And in the case of relational databases that we use for our experiment, the lineage is defined as the set of all and only the tuples in the input database that have a role, whatever that may be, in the query that produced the output. So, for our experiments, what do we need? Well, we need two things. We need a database to cite, and we need the citations to this database. We use as a database the IUFAR Guide to Immunopharmacology, which is a quite famous database in the medical field, curated and maintained by people at the University of Edinburgh. It contains information about disease, about genes, ligands, targets, things like that. It is quite known, it is maintained, it has its own website and web pages that are used by researchers. For the citations, we use the papers coming published in the British Journal of Pharmacology. And why exactly this journal and not another one? Because it has a very nice policy, at least for us. If you want to publish a paper in this journal, and this paper uses data or information taken from web pages of the IUFAR database, you need to put the URL of this web page in these papers. It is mandatory. So we can use these URLs to reverse engineer the SQL queries that are used to automatically produce the web pages of IUFAR. So we can, with this process, with a little bit of reverse engineering, we can obtain something which is as close as possible to real-life queries, to real-life data citations. And so we perform our tricks, we do our computations, and this is one of our outputs. What you see here are 3 heat maps. Each heat map corresponds to one relation in the IUFAR relational database. Each cell is a tuple, and the color represents the quantity of credit that we were able to annotate to these tuples. So we were able to annotate this information, this credit, to each tuple. The more the credit, the darker the shade of color of the tuples. So as you can see, we were able to annotate this database to find the elements that are relevant in the context of citations defined by the papers published in the British Journal of Pharmacology. And in particular, it is interesting to note, at least for me, that there is a Pareto distribution here. Few tuples are the ones that are used the most, that have the higher impact in the research carried on in the British Journal of Pharmacology. From another point of view, we have this slide. So what is the idea here? In the same way in which when we cite a paper, we are also assigning one citation to the authors of this paper, we can do the same thing with credit. So when we assign credit to data, we are also able to assign this credit to the authors of this data. We are able to do this because this information is present in IUFAR. We know the authors of the data. So on the left-hand side, we see a radar plot with the top 10 authors who receive the highest quantity of citations coming from the papers from the British Journal. On the right-hand side, we see the top 10 authors credit-wise. And as you can see, if you receive a lot of citations, it is not necessarily true that you also receive a lot of credit, and vice versa. Now, I didn't go in the detail on how we compute credit, how we distribute it, but the idea that I want to convey here is that credit behaves differently from citations. What does this mean? That there are certain citations that are more impactful in the generation and distribution of credit. There are some cases when a citation is more important, generates more credit for its authors than other types of citations. So credit is able to reveal a different perspective, a different point of view in the study of bibliometrics, in the study of research impact of data and its authors in a context, in this case, the context of a British Journal of Pharmacology, but we could extend this to other contexts, other situations. So to conclude, I already explained a lot of conclusions. So we see how data credit can be used as a new tool to use alongside traditional citations. It is flexible. It allows to solve some problems of traditional citations in the context of data. It allows us to understand, as we see, some interesting points inside a database, the so-called hotspots of a database. And since now we have this information annotated to the different parts of a database, we can carry on different types of tasks. So for example, the data pricing task, when I want, for example, to give a price to my data. If someone wants to buy my data and I put a lot of work in my database, but maybe I can sell it to this person. And with this annotation, with this credit, I can understand or help the process of understanding how to assign a price to my data. And this is all from me. Thank you very much for your kind attention.
Thank you very much, Dennis. Perfectly on time. Any quick questions, since it's we are a little bit late, but still within the time frame. Okay. If no, just a curiosity. I know you skipped all the details about how you compute the credit, but how about, is there any negative credit in your model?
For now, not. Mm-hmm. But we can put it we can another task. So I talked about data pricing. There is another type of task that is called data reduction or something like that, which is studied by Tova Milo, for example, among others, and is the task of removing data from a storage. So maybe you have an evolving database that is becoming very big. You don't want to keep all that stuff. You may want to get rid of some data. You may think about introducing negative credit to understand not the hotspots, but the cold spots, which can be, for example, removed.
Interesting. Thank you very much. Okay, I think we have ended this session about text analysis. I'm not sure if we want to do some break, like 5 minutes break before we start. I'll ask to the organizers. Maristella is already ready with the section.
Yes, so I can meet the speakers and organize the section.
Yes.
2 minutes would be useful.
Great, thank you. So I'll leave you the floor. Thank you.
Thank you very much, Giorgio. So I would like to check if the speakers are able to present their presentation. I see online Tanya Svarre, if it's correct, the pronunciation is correct.
Very good.
You. Do you like to try and see if you are able to present your presentation?
Yes, I'll do it now.
And in the meantime, I see Eleonora on the line, so okay.
So do you also see the notes on the side?
And I don't see the picture by the moment, but I see that you have started the process. Probably is a problem of distance, I don't know.
Yeah, let me see if I can switch to another.
Probably it's better if you can.
Another window.
Let's see. So I see the perfect.
Okay.
Perfect, Tanya.
Great. Thank you.
I can see, I think. So it's fine. Good. And since you are the only author, I think you are going to present the paper.
Okay. Now?
Is the second paper? No, it's the second paper in the list. Yeah. I see Eleonora Bernasconi online. Eleonora, are going to present your paper together with the other colleagues or by yourself? Yes.
Okay.
Eleonora? Perfect.
Okay.
Okay. And you are the presenter.
Okay, I'm starting. Okay, sure.
Okay, I check for the third paper. So Eleonora is the first presenter. Afterwards, there is Tanya, a second paper. And I have seen online Bruno Almeida.
Hello, yes, I'm here.
Okay, are you going to present the paper?
Yes.
Perfect. Do you like to check if you can share the screen, please?
Does it work?
Perfect. Okay, I can see your presentation, so it works. Thank you very much. And Bruno, are you going to present by yourself the paper for all the other?
Yes.
Perfect. Yes. Okay. I don't know if we like to wait 2-3 minutes or if you like to start. Let's see if the organizers like we wait some few minutes. Gian Maria, if you are online.
Yeah. No, I think we can start.
We can start, so it's better if we can start. Fine. We are a lot online, so it's okay.
Yeah, I think
so. Welcome to everybody to the section number 6 that is devoted to the DL services. We are 3 short papers that are going to be presented. I would like to invite the authors to present for 8 minutes, let's say, so we have some time available for questions at the end, for at least one question at the end of your presentation. The first presentation is by many colleagues, but Eleonora Bernasconi is going to present for all of them. Please, Eleonora.
Thank you. I am Eleonora Bernasconi, a PhD student in engineering in computer science at Sapienza University of Rome. And in this presentation, I will talk about the NOTAI project and its goal. I will present you the main knowledge bases in the digital humanities research field. I will talk about the challenges and the issues in this research field. I will present you the NOTAI graph solution and the technologies behind it. I will describe the system and I will show you a practical example where I demonstrate how NOTAI graph can help ancient documents and symbols researchers to find historical implication through a specialized tool. Finally, I will talk to you about the future works. This work represents an essential research step to run to the main challenge expressed in the European NOTAI project. Investigate the graphic symbols to capture all the possible historical implications by studying their graphic execution and their models. With NOTAI graph, we can achieve this by building the NOTAI knowledge graph and the NOTAI graph interface. Building the NOTAI knowledge graph, we want to share a common understanding of the structure of information among papyrology researchers, enable reuse of domain knowledge, and make domain assumption explicit. While building the NOTAI graph interface, we want to explore all the knowledge extracted in the knowledge graph NOTAI, allow researchers to search and explore relations and connections between resources, make historical implication, and finally discover new things. Many works face the challenge of creating semantically enriched knowledge bases to view data under new perspectives and discover hidden implications by searching and visualizing those data. This slide lists and describes current use of semantically enriched knowledge bases in the digital humanities. For example, Pleiades contains data about the ancient world geography. This system provides a semantically enriched formats of its data, but doesn't allow the query of those data through a Spark endpoint. Then papyri.info contains an electronic corpus of ancient papyrological documents and related materials, but like Pleiades exposes its data but doesn't allow the query through a Spark endpoint. Trismegistos is a metadata platform for the study of text from the ancient world. Contains documents, people, and places, but do not currently provide a data expert feature. It does share its data by papyri.info in the form of periodic database dump. All of them have embraced the link open data as a means to connect their data to the broader digital cultural heritage infrastructure, but have at the same time avoided the complexity of attempting to represent the full range of data as RDF. Some of them have tried, but it's impossible to access their resources without spending a long time preprocessing, mapping, and integrating with other vocabularies and knowledge bases systems. Today, there isn't a knowledge base about ancient symbol for papyrology researchers, and there isn't a RDF schema and a tool to represent completely this domain. The main feature of NOTAI graph is the visualization of the knowledge graph-based original contents inserted by researchers and the full integration and accessibility of these contents. In this slide, I will explain what are the technologies that allow us to build the NOTAI graph tool. The Resource Description Framework, RDF, is a standard model for data interchange on the web. RDF offers the ingredients necessary to build a giant global graph of data, where individual documents describe part of a data graph that can be interlinked to form a cohesive global graph of data. While RDF terms are used to identify resources, RDF triples are used to describe resources. Vocabularies provide a set of classes and properties to describe a given domain user the RDFs and out standards, and make data integration easier by reducing diversity in describing things. For example, in the NOTI graph, we have defined one new vocabulary and we used 8 existent vocabularies. New vocabulary regards, for example, symbols, documents, elements, shape, and positions of the symbols in the documents. And existent vocabularies regard the images of the symbols, coordinates of places, description of the resources, etc. In this slide, I present the design of the NOTI graph system, able to offer a novel service, discover historical implication of graphic symbols. The papyrology researchers insert and update data in the NOTI database through the NOTI interface. Then we start from querying those data to extract all the relevant data in the papyrology research field. Subsequently, we analyze data and build software to automatic processing this data. We have defined a vocabulary and reused existing to describe all domain. We apply the data model to define the RDF scheme of all data. And finally, all semantic data will be accessed either directly through a web service, a Sparkle endpoint, or through the visual user interface. Although the existing work with aspect of the system proposed here, our system is novel in being designed from ground up to offer the knowledge graph-based access to the ancient documents and symbols. The user interface is novel in adaptive visual in data exploration as a means to search in a corpus of content. For each step, there are existing components that we adopted or new components that we are developing. For example, for the triple store, we're using Blaze Graph. To map in data, we use a Python tool which preprocesses, clean, and maps the CSV output of PostgreSQL to RDF standard. The web frontend is developed using the React framework for its modularity. We reused the Arca frontend and adapted it to this context of use. I want to show you a video to discover historical implication with the NOTI graph tool. For example, we are looking at 2 resources. In this case, are 2 documents. Then we open the tracepath tool component to looking for the elements in common of these 2 types of resources. We discovered that the provenance of both is undefined and both are documents. Then we can continue to browse the system and we can drag and drop all the resources from the results that we have found. For example, we can explore the loan contract, that is a document. We drag on the board the papyrus, which is the provenance of this document. And then we are looking for all the documents coming from the papyrus. And we can, this type of researches on people, places, documents, symbols, etc. In conclusion, in this work, we present the vocabulary construction that describes the domain of ancient documents and the symbols in them. We also presented a visual search tool adapted to this context. The single search for a term or parallel searches that show resources connected by semantic relationships support our hypothesis, find a historical implication between multiple instances of classes or between documents, symbols, languages, places, etc. The next goal concerned the extension of the vocabulary to all the elements of the NOTI relational database, the construction of an adapt tool to show and search documents based on geographical location, integration with other existing database and knowledge graph, like Trismegistus, Pleiades, etc., and an evaluation of the system with a classroom of students. Thank you for your attention.
Thank you, Eleonora. Any question from the audience? We have time just for a short question. Any question? So I have a question. Eleonora, I've seen that you have used many different tools for the different aspects to be addressed by your implementation. Have you had any problem in the cooperation, in the interoperability of those tools? any specific problem to
And
address?
now we haven't found any problem to integrate all of these technologies. This is one of the main particularity of our pipeline, that can integrate all of these technologies in an automatic way. This is the main function of our system.
Perfect. Thank you very much for the
Thank you so much.
Thank you. So now the next paper is going to be presented by Tanja Svarre from the Aalborg University in Denmark. She's going to present a paper on the labeling on academic library websites. Please, Tanja, if you like to share the screen and start your presentation. You have 10 minutes from now.
Yeah. Oh, sorry.
It was visible. It was visible.
Okay, okay.
It's enough if you can make full screen.
Yeah.
The presentation. Perfect.
Yeah.
Perfect.
Okay. So I'm Tanja Svarre, and I'm from Aalborg University in Denmark, and I would like to present some work I did on the labeling of academic library websites. So the background for this study is that the vocabulary problem addresses how the same content can be described in a lot of different ways depending on the user's point of view. So we can use labeling to minimize the vocabulary problem by representing content and guiding users toward relevant content. However, previous studies describe how users are challenged by the terminology and labels of library websites, and it ends up actually influencing on their perception of usability. So we know that the challenges count, for instance, what are the specificity of the labels, what is their general understanding of the terminology used. Usually these studies are representing one library and a study of how users are using one library. So with this work, we would like to look across libraries to see what is the terminology used, what are the labels, and what characterizes them. So to do that, we looked into the pool of Danish research libraries with special obligations. So they may have some archive function or the like, but usually they are connected to university libraries, university college libraries. It can be museum libraries, and there are some national institutions like the National Statistics Office and so on. So in total, we have 22 of these libraries, and they cover a lot of different topics, like general university topics, professional bachelor institutions, educations, museums covering design, movies, and working history. What we see when we look at these libraries is that some of them have their own websites, while others are sort of incorporated into their host organizations. And that's what you see in the left right corner. We see that University College, which is the second one in the model, all of them have their own websites. So does the uni/other category, which is the national library, but it also serves as university library for Copenhagen University. So all of the other institutions or libraries are hosted by their institutions, which when you extract labels from the websites would reflect in the labels that we find. So with this study, we're interested in seeing how do these academic libraries actually use labels for communicating with their users. So what we did was that we used a web menu crawler that extracted the labels from the websites. We did that last year. and we crawled the Danish versions of these websites, because what we usually see is that the English counterparts holds less information. It's a summary usually of the information. But crawling the Danish websites also meant that there was some cleaning to do afterwards, because the crawler didn't accept Danish special letters. So we had to go through the files. It extracts CSV files. So we had to go through them and see where do we have missing letters. So there was some cleaning to be done. With these files, after cleaning them, we did two types of analysis. We did a content analysis to identify how many labels are actually used, what is the length of these labels, and how many terms do they include. Next, we did text analysis using NVivo. NVivo has a text analysis function that enabled us to identify what are most frequent terms, but it also enabled us to do a cluster analysis to see, on the basis of term occurrences, which libraries are more similar than others. And I will present what we learned from these analyses now. So as regards the first point, we saw that when we look into the number of labels, they had these 22 libraries had an average of approximately 100 labels on their starting page. But we also see a large variation, because the lowest number of labels is 29, whereas the highest is 378. So there's a large variety within these libraries. Also, when we look at the length of labels, there is also some variation, but a mean of approximately 17 characters in each label. And regarding number of terms, we see that they have a mean of 2.25 terms, but also with some variation, going from, of course, at least one term to up to 9 as the highest. So when we remember that that some of these labels are incorporated into their host institutions and other are not, it would be relevant to see if that actually influences on the number of terms. So we did an independent sample t-test to see if there is any difference between these types of libraries, but we couldn't find that. So it seems that the variation is not caused by whether they are included in a host institution or not. So when we look at what are most frequent terms, I have two figures here, and if we look at the one on the left-hand side, we see that core services like search, library, research and education are highly frequent terms across these library websites. It illustrates that a lot of the libraries offer services to students and researchers, but also that some of the libraries are incorporated within the host institutions' websites, and that the institution labels have also been crawled by this menu crawler. So that means that we see institution names in the table, like for instance, DTU, STU, and CBS, which are Danish universities. But when we then turn to the right-hand side of this slide, we see the sort of distribution of these terms across the libraries. So here it's clear that the institution-specific labels that we just mentioned are used by one institution only. So it's not a general thing to have these institution names. It's one library at the time who represents these. But what is general to all of the institutions, or many, is now the term library, its search, its contact information, its wayfinding, its research, and so on. So it's clear that we look at academic libraries here from these purposes that they present. If we then turn to the cluster analysis, what we see here is the result of the cluster analysis. And several things appear from this model. So first of all, we have two overall clusters, and the upper cluster, which would be this one, contains all of the libraries within university colleges. So the similarity between these libraries suggests that the purpose and the target group actually influences on their choice of terminology. If we look to the second or the lower large cluster of this analysis, we see the remaining libraries, which is university libraries and libraries with other purposes. So the picture is less clear, but still some observations can be made. For instance, we see the Danish Movie Museum and the Design Museum, which I have put a red circle around, to being in the same cluster.
Excuse me, Tanya.
Yeah.
But, we are going over time.
Okay, I'll hurry.
Try
so,
to.
Yes, I have one slide more, so I'll hurry.
Thank
you. So they have the same cluster as another museum, which is the Finnish Museum Library. The same is the case if we look further down. This is the two architecture schools of Denmark. So there are some similarities due to specialties when we look at these cluster analysis. So to sum up, we see a lot of different purposes within these libraries, but where previous studies have identified this prevalent library jargon in labeling of library websites, it doesn't seem to be an issue when we look at these libraries, but of course we would need to ask the users as a follow-up on this to see, is this consistently good or consistently bad? But there is a sort of joint terminology here. We also see in the cluster analysis some similarities between related fields. So it would appear that similar libraries tend to draw on the same terminology within these domains that they represent. So it could be a step towards reducing the vocabulary problem. But again, we would need to ask the users whether they actually make sense of this. And of course, in the end, we would have to mention that this holds a sample of 22 libraries. So we would need to elaborate this further to see if this picture actually would appear in the same way if we look at more libraries in general. So sorry for going over time, and thank you for your attention, and I'm open to questions.
Thank you very much, Tanya, for your interesting presentation that can be of interest also for other languages, for other countries in Europe. I'm sorry, I have to pass to the other presentation. Please, if somebody wants to have information from Tanya, if can use the chat or contact her directly. Thank you very much, Tanya, also for your presentation again.
Thank you.
So I pass the floor to Bruno Almeida. He's from Portugal, Lisbon. He's going to introduce us the development of a thesaurus. Bruno, if you like to start your presentation. The floor is yours.
Thank you. Good morning, everyone. So I will do a quick presentation.
Not so clear, Bruno, sorry.
Sorry?
The voice, your voice is not so clear.
Is it better now?
Probably yes, thank you.
Okay, sorry.
Thank you.
Okay. So I will do a quick presentation on the ongoing development of the Rocio thesaurus. So I have a background in humanities, more specifically in linguistics. And my colleagues who co-authored the paper, Nuno Freire and Daniel Monteiro, have backgrounds in computer science. So just a quick word about Rocio infrastructure. So it's the Portuguese representative of the RAIA, which, as you probably know, is the digital research infrastructure for arts and humanities in Europe. RUSIU is made up of a consortium, of 7 institutions, public, academic, and private sector institutions that provide access to metadata descriptions of digital objects in social sciences, arts, and humanities. And this consortium is coordinated by the Nova School of Social Sciences and Humanities from Lisbon, Portugal. There is a platform that is still under development, which will aggregate the metadata descriptions of digital objects provided by the members of this consortium. And also the platform will provide services based on these data sets, which will be free and open access to the community. So some of the services that we will provide, which are still under development, will consist of simple and advanced search on the aggregated data sets. Also, we will have a virtual research environment in which researchers can select certain documents and make lists, bibliographic lists, and so on, and notes. We will have a service for digital exhibitions and collections, also curated by researchers of the Nova School of Social Sciences and Humanities. And also we will carry out training sessions and workshops, webinars, and so on. So with regard to data management and the platform, there is a DSpace instance which has already been deployed that will provide access to sharing and reuse of the datasets aggregated and produced in the platform. These datasets will be described. Sorry, there is something, an automatic function here which I'm not. Okay. I think now it will be better. Sorry for that. So the data sets at the dataset level, so they will be described in DCAT2, which is a W3C recommendation for interoperability between data catalogs and datasets on the web, which has enough detail for data exchange with content aggregators, such as the scientific open access repositories of Portugal, the open air repositories at European level, and also the European data portal. With regard to individual items, they will be described by reusing an application profile of a well-known standard, the Europeana data model, which has been developed for a similar initiative to RUSIU, which is a directory of digital repositories in Portugal. So the RUSIU vocabularies, at this time, we have several that are in development. They are basically a set of Scotch concept schemes with the purpose of supporting content discovery and data management in the platform. There are, at this time, vocabularies for topics, which is the RUSIU thesaurus, that I will talk a little bit more in the next slides. Also, there are vocabularies for agents, places, and periods. And for this, we use subclasses of authority in BibFrame, which is an ontology for bibliographic description. So, the methodology that we are generally using for developing these vocabularies is based on ISO 25964, which is the ISO standard for thesauri for information retrieval. We have deployed a tool for managing and developing the vocabularies, which is Workbench 3, a remarkable tool, by the way, developed at the University of Rome, Tor Vergata. And for publication and browsing, we are implementing Scosmos, which has been developed by the National Library of Finland. And so the steps, I will not go into detail here, but you can see the steps which are basically taken from the ISO standards. At this time, we are in the construction phase. We have already assembled relevant vocabulary resources. We have already identified reference thesauri and so on that can be reused, especially those that are made available as linked open data. And at this time, we are looking at strategies for involvement of domain experts from the several research units at the Nova School of Social Sciences and Humanities, and also information specialists, librarians, and archivists from the several institutions that make up the consortium. So, with regard to the Rocio thesaurus, we are, as I said, doing this development based on reusing third-party vocabulary resources, such as lists of indexing terms provided by our partners, and also reference thesauri that are made available right now as linked open data. In our vocabularies, as a minimum requirement, we want each concept to be lexicalized by Portuguese and English terms. The Rocio thesaurus, as I said before, is or consists of topics, so it includes mostly general concepts in terminology. These are classes or groups of things that are usually denoted by common nouns such as poets, pottery artifacts, or noun phrases. But it also includes some individuals, such as names of disciplines, sociology, for example, and art movements, surrealism. The Rocio thesaurus is linked to the other vocabularies, for example, by supplying URIs for modeling types of agents or types of places, which is similar to what the Getty Art and Architecture thesaurus does with their place gazetteer, which is Ulan, if I'm not mistaken. Oh, no, Ulan is for agents. It's the thesaurus for place names or geographical names. And so the Rocio thesaurus is also being aligned with external vocabularies that are relevant in the arts and humanities, mostly the Getty AT, but also the Raya backbone thesaurus, which is a meta thesaurus with very general concepts that can be reused or further specialized for domain-specific thesauri, which is our case. And this is done by using the SCORS mapping properties, such as exact match or close match. And this alignment, as I specify in the paper, is carried out through an alignment tool for ontologies and vocabularies, which is Silk Workbench. So here are some of the preliminary results. Of course, these numbers are already out of date, but so far we have defined top-level concepts or hierarchies of concepts, which are agents, places, temporal entities, physical objects, and conceptual objects. And this was done, this was carried out by doing a review of ontologies and reference thesauri, such as the aforementioned BBT, but also the CRM ontology and Dolce.
It would be important to wrap up if you can.
Yes. So here you can see some relevant metrics that were extracted from VocBench in December. At this time, we are closing on 4,000 concepts, and we have close to 600. Well, at this time, it will be more like 1,000 links to the Getty AT. And with regard to the role in data management, we find that Rocio will help, or in fact, our vocabularies will help Rocio to comply with FAIR principles by facilitating rich metadata for descriptions, which is a FAIR principle, and also by adopting vocabularies that are documented and resolvable using URIs, which is another FAIR principle. And so the data sets will be linked to the vocabularies by means of these properties that you can see here, the cat theme, DC term spatial and temporal, probably also the type property, which of course will describe data sets with concepts from the vocabularies. Thank you very much for your attention, and I'm open to questions or suggestions that you may have.
Thank you very much, Bruno. If there is a very, very short question by anybody, I don't see any hands. So I think it's a very interesting work going on. Probably in IRCDL next year, you can introduce us next results, because I imagine then you are going to publish it by September this year, if I'm correct. Is correct?
Yes, yes, that is correct.
So your plan is by September. So we are looking forward to have information from that. Thank you.
Thank you very much.
Thank you very much to all the people that have made the presentation of this section. And I'm closing the section. Thank you.
Thank you, Maristella. And we are on time, since it's time for the closing, but the closing will be very fast. So I thank all the people participating and the presenters and all the other chairs, sia Antonella, Paolo, Giuseppe, and Stefano in random order. And well, let's say that see you next year. We don't know how, where. So I think we do not have, actually, we do not have any announcement right now, but that IRCDL will exist also next year, that's for sure. And we'll see how the situation evolves. For sure, we have to keep going with the discussion we started last year and we continued in 2020 and 2021 about the future of DL and the future of IRCDL, and probably a new format for the conference, slightly different. Let's see when we can do a conference in presence to implement some of the ideas that we discussed and we have in mind. This year, I think, was a nice conference. We had nice papers. Online participation is always not easy to understand how it went, but there was participation, and I think it was good enough. Not perfect, because we all prefer to meet in person, but that was not an option this year, as we all know. So if anybody has something to say, it's an open mic. Otherwise,
me, Stefano. This is Stefano. And Gianmaria, I would like also on behalf of the other chairs to thank you so much for driving our effort during this period.
Absolutely.
And of course to all people from Padua, because even if it was a virtual conference, there was also a real effort for the organizing committee. And so thank you very much for making this in these hard times, this event a success. I think I can say it was a success. So thank you very much.
I joined Stefano. Thank you, Gianmaria. And also everybody else from Padua.
Yeah.
Grazie a tutti.
Grazie anche da parte mia a tutti.
Direi che
hanno fatto un ottimo lavoro, perché lavorare sempre a distanza, eccetera, e avete raccolto tanti buoni paper quest'anno, veramente interessanti e molto interdisciplinari, molto interdisciplinari.